Hey guys, hope you are doing well. So here we have a grade 12 chemistry exam that was written in June 2022. 150 marks, 3 hours. So the video the paper you can download it in the description below. And if you would like to, so you can download the paper. I got a bit stuck with what I was trying to say there. So download the paper and then you can see what questions are coming up. And then you can fast forward to the specific place where you want to go. Or you can just sit and go through the whole exam paper with me. Awesome, let's get started. Which one of the following compounds has the lowest melting point? Okay, so now let's talk about melting. Okay, so melting is when you go from a solid to a liquid. Okay, now if you look at things in the solid phase, are the particles close together or far apart compared with a liquid? Well, they're closer together. Okay, so this is what things would look like in the solid phase. In the liquid phase, they would be more apart. Okay, so there are little forces in between these molecules, and those are intermolecular forces. Intermolecular. Examples: London forces, hydrogen bonding. Okay, why am I making this sound like a song, like a riddle? Guys, I was not planning that. Okay, so it's like London forces. Pause. Hydrogen bonding. Pause, because if I say it too fast, it starts sounding like a riddle. Hydrogen bonding, London forces. Okay, so yeah, we get intermolecular forces. You probably think I'm absolutely nuts. I think I am too. Okay, so we've got these intermolecular forces. Over here, we also have intermolecular forces. Okay, to be able to convert something from a solid to a liquid, you need to obviously try convert it from like this to like this. So in both scenarios, we have intermolecular forces. However, the intermolecular forces for these ones are much stronger because they're much closer together. You see, the molecules are much closer together. So when you melt something, you add energy in the form of heat to try and overcome these intermolecular forces and allow the molecules to move further apart. Okay, so once again, how do we go from here to here? We need energy. That energy is in the form of temperature. Well, it's actually in the form of heat, but we can measure the heat by looking at the temperature. So the higher the temperature, or the more, let me slow down and say this nicely. You need heat to be able to give energy, to be able to separate these molecules so that they move further apart and they go into the liquid phase. Okay, so if you have molecules where these intermolecular forces are very, 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 very strong, then does that mean you would need more heat or less heat? Well, then you would need more heat because you would have to use more energy to separate them. However, if you have molecules that have very weak intermolecular forces, then it will be very easy to separate them, and you won't need as much heat, and so the melting point would not be as high. So it says here, which of the following compounds has the lowest melting point? What that means is the lowest melting temperature. So the lowest melting temperature. So what they're actually saying is, which of these is the easiest to melt? Okay? So the ones that are the easiest to melt, meaning that they have the lowest melting temperature, would be the ones that have the weakest intermolecular forces. So we need to look at these and think about which ones have the weakest intermolecular forces. So we know that hexane is a 6-carbon alkane. And then if you had to draw another one, why do I always draw 2? It's because we're looking at the intermolecular forces, which is the forces in between the molecules. Okay? If you had to look at ethane, there's only 2. If you had to look at butane, there's 4. And if you had to look at octane, there's 8. From our studies of organic chemistry, we have learned that longer chains have stronger London forces because of the let's make some notes here. So we've learned that longer chains equals stronger London forces. Why? Due to a larger surface area, or you could say larger molecular mass. Okay, I'm not going to go any further because we have spoken about this before. Due to larger surface area, or you could also say larger molecular mass. Okay, so the octane is going to be more difficult to separate because the London forces are quite strong. Ethane, however, is going to be super easy to separate. Because the chain is shorter, there's weaker London forces, and so it'll be easier to separate, and so it would have the lowest boiling point. And so that is our answer. It'll be the easiest to separate, so it has the lowest melting point. Okay, I hope that makes sense. When CH2 double bond CH2, let's draw that out. CH2 and another CH2 with a double bond. Okay, so that's an alkene, right? Let's remember that. That is an alkene. When that is converted to CH3, okay, CH3, okay. So what we can see is that we've just added on hydrogens on either side. Did you just hear what I said? We added on hydrogens. So we added hydrogen. So it's not hydration. That's when you add water. It's not hydrolysis. That's something to do with haloalkanes and alcohols, or haloalkanes becoming alcohols and things like that. It's not halogenation. We didn't add any halogens. We added hydrogen. It's hydrogenation. Which one of the following compounds in solution will change the color of bromothymol blue? Okay, now if you're reading this and you're like, wait, what? Well, I'm also thinking, wait, what? This is not a common question. I would not expect many learners to get this. Yeah, so we'll go through it, but it's not a good question. I mean, how are we supposed to just randomly know this? Like, that's pretty crazy. So the only thing I think I really need to mention, I mean, it is technically in most of your textbooks, they talk about bromothymol blue in the chapter of acids and bases, specifically where they talk about indicators. We know that bromothymol blue, it is an indicator. Okay, so it'll change colors in whether you're adding an acid or a base, for example. So what we could do is just look at some of these molecules and just find one that's an acid or a base. Okay, so straight away, if you had to go do this one, that's probably like a ketone or an aldehyde because it's just got that one oxygen, so it wouldn't be that one. But then I look at this one and I see that C double bond, well, C double oxygen H, that Cu. Now that, my dear friends, is typically what we should be used to as a carboxylic, say the next part, acid. So it's going to be that one because this is an acid. And we know that a bromothymol blue is a type of indicator. You know, you get the other ones like phenol, naphthalene, bromothymol blue, methyl orange. They're all indicators. So we should expect that they will change colors in the presence of acids, bases, things like that. Okay, so this, and then this one only has one oxygen, so that's probably a ketone. And then this one has two oxygens, but it's somewhere randomly in the middle, so that one's probably an ester. But this one has that beautiful C double bond, not double bond, Kevin. Come on, bro. C double oxygen hydrogen. And so this one would probably be this one is a carboxylic acid, sorry, and so this would be your answer. Two different samples of impure calcium carbonate, CaCO3, of equal mass react with sulfuric acid. The graph below shows the volume of CO2. Okay, so let's quickly get a little rundown. So we know from grade 10 and 11 that you've got these main acid-base reactions, okay? I've mentioned them before. You know the ones that say something like, if you take an acid and you react it with a metal, then you get a salt and hydrogen gas. If you take an acid and you react it with a metal oxide, then you get a salt and water. You know these ones, hey guys, I'm not going to go through all of them, but one of them says that if you take an acid and you react it with a metal carbonate, then you get a salt, water, and CO2. And so here we have an acid, which is sulfuric acid, plus a metal carbonate, calcium carbonate. That's a metal carbonate. Then you produce salt, water, CO2. So we shouldn't be surprised that they're saying that the graph below shows the volume of CO2. And remember, CO2 is a product in this reaction. It's a product. So we can see that its volume increases as the time goes on. Okay. So two different samples of equal mass. Okay. When compared to reaction number 2, which one of the following statements best explains the curve in reaction 1? Okay, so they use equal mass of calcium carbonate. So let's see. Is the temperature higher in reaction 1? No. I mean, a larger temperature would make it go faster. So look at reaction 1. It's going slower. See that? If it was faster, it would go like there. Okay, so it's not that one. It's not going to be the surface area. It's going to be, you got to think about this carefully. We are producing different amounts. Can you see that? We are not, if it was just a temperature, the graph would go faster and then it would just go to the same place, for example. If it was surface area, it would just go faster, but then it would still go to the same place. But the fact that we are ending up lower, that tells me it's got to do with the amount of something. So in reaction number 1, is there more calcium carbonate or less? Well, think about this. If you have less reactant, then you will produce less product. So there's less, now be careful in the answers, there's less calcium carbonate in this one. Okay, there's less calcium carbonate. But they told us that it was an equal mass of sample. Okay, that's what they mean there. They mean that in reaction 1, and in reaction 2, the sample size is the same. The sample size. So maybe they gave you 10 gram of sample, then in this one they also gave you 10 gram of sample. However, there are different amounts of impurities, because check here, they're saying the amount of impurities is greater in that one, or the amount of impurities is greater in this one. Now the impurities is the stuff that doesn't react. So I think that in reaction 1, there's more impurities, because let's say there's 6 grams of impurities, and then in this one there's only 3 grams of impurity, for example. Then if you have 10 gram sample, and 3 grams is impurities, then how much calcium carbonate did we actually have over here? Well, there should be 7 grams of calcium carbonate. Then how many grams of calcium carbonate would you have here? Well, 4 grams of calcium carbonate. So I suspect, this is the answer. In reaction number 1, there's less calcium carbonate, but that means that there's more impurities. So the amount of impurities is greater in reaction 1. The equation below represents a hypothetical reaction. A plus B goes to C. The activation energy for the reverse reaction is 110. Okay, which one of the following is the activation energy for the forward reaction? Okay, don't just say 110 or don't just say 50. Let's go draw this out. So we know that you've got these diagrams, okay? Now it could either go like that or it could go like that. You know where it ends up. Okay, wait, let's do this properly. So it could either go like that, or it could end up higher. Okay? Now, if you look at this, we know that if delta H is negative, if it's a negative value, that stands for exothermic. Okay? And that's for the forward reaction. So an exothermic would look like this. It always ends up lower down. Okay, now that's for the forward reaction, going this way. Now they told us that the activation energy, for the, well, let's first do this. Let's just say, they said that the delta H is a negative 50. So you can choose whatever number you want over here. Any number you want. Let's just choose 20. Then this down here would be negative 30. Why? They said that the delta H changes by negative 50 from your reactant to your product. And you can choose any number you want. It doesn't matter, okay? They then tell us that the activation energy for the reverse reaction is 110. Okay, so we're going to go up 110. Remember, reverse means this way. Okay? Forward means that way. So the reverse reaction activation energy is 110. Remember, the activation energy is from this part to the top. Okay? But I'm not looking at it here because they said the reverse reaction, which goes that way. If they said the forward reaction, then I would look at this part. Okay, but I'm going to say that this is 110. Okay, so if you go from negative 30 and you add 110, then that means you would be at 80 over here. Okay, and so now if you read off these values, you're going from 20 up to 80. If you so your activation energy for the forward reaction would be when you go from here to here, and so that would be 60, and so the answer is B. Now you could have chosen any of these two numbers, it would have given you the same answer. A reaction reaches equilibrium at 25 degrees in a flask according to the following balanced equation. Which one of the following will change the color of the mixture from pink to blue? So they want to know what will cause the reaction to be favored, or the forward reaction to be favored, because then it goes blue. Okay, so I'm going to go through some of these. I won't go through all of them, but let's say, for example, let's say for this one, cooling the flask. So if you make the flask cold, then what is the system going to try to do? It'll try to make the flask hot. Now you need to understand that this symbol here stands for endothermic because it's larger than 0, so that's endothermic, and that is for the forward reaction. That is what they're trying to tell you. Wherever they put that, that's the forward reaction. So what they are trying to tell you here is that the forward reaction is endothermic. That's what they're saying. Now remember that endothermic makes things cold. So therefore, forward reaction, when forward is favored, the reaction becomes cold. Okay, but now they've cooled the flask. So some students get confused with this. So someone comes along and they decide to make this flask cold. So what is the system going to try to do? The system is going to try to make the flask hot again. Remember, the human being changes the temperature and they made it cold. The system is then going to try make it hot again. So how would it do that? Well, it's not going to go forward because forward is endothermic and endothermic means cold. So when the forward reaction is favored, the reaction becomes cold. But that's not what we want to do. The system wants to try and make the reaction become hot again because someone changed it to cold. So the system is going to try and make it hot again. Okay, so I'm not going to go through all of the options, but let's just talk about some of the important ones. I'm going to start with this one over here, okay, because some learners get really confused with this. So the first thing you look at is this. You need to understand, does that mean endo or exo? That means endothermic. Okay? And you see, I've mentioned this before. Whenever they write it over here, they are talking about the forward reaction. Okay, so we can say that the forward reaction is endothermic. Now, what does endothermic do? Does it make things hot or does it make things cold? Endothermic makes things cold. Okay, so now you got to think about this carefully. Someone, a human being, comes to this reaction and they do this. They make the reaction cold. Now, the system does not like that. The system, according to Le Chatelier, will always try to oppose this. So if a human being comes to this reaction and they make it cold, then what is the system going to try to do? It's going to try and make it hot. So how does the system make it hot? Well, it's not going to go forward because we just said that the forward reaction is endothermic and endothermic makes things cold. So it will actually go in the reverse direction. Because then it goes exothermic, which makes things hot. So this answer is not going to work. B cannot work because we're trying to find which of these is going to cause the forward reaction to be favored. Okay. It's not going to be this one because there is no Na inside here and there is no OH that we can see over there. Okay, let's look at this one. Now that is a salt, ammonium chloride. You got to think of that as NH4 plus and Cl minus. That's what it actually is. So look at this. We're adding some of this. Ooh, there we go. So according to Le Chatelier, if you increase the amount of Cl minus ion, the system does not like that. Remember that whatever the human being changes, the system always goes against that. So if someone comes along and adds Cl minus, that's going to make this concentration go up. But the system does not like that. So what is the system going to try to do? It's going to try and make this amount become less. How does it do that? Well, it goes in the forward direction, because when it goes in the forward direction, your reactants become less and your products become more. And so the answer is D. Dilute nitric acid is added to distilled water at 25 degrees. Okay, how will this... Okay, so nitric acid is... I'm not sure if we're going to need this, but nitric acid is HNO3. And they said that they've added it to water. Okay, now we know that if it's an acid, when you add it to water, it ionizes. Okay, remember, this is an acid, so it gives away its proton. It gives away its proton to the water molecule, so the water molecule now ends up with 3 hydrogens, and then this molecule ends up with 1 less hydrogen. Okay, now it says, how will this affect the hydronium ion, which is H3O plus concentration? Okay, so look here, this is H3O. Okay, how that, and then it says, and the ionization constant of water. Okay, well, we know that the ionization constant of water is equal to this multiplied by this, but it is a constant at 25 degrees Celsius, so it cannot change. Okay, so that's not going to change because at 25 degrees it's a constant. Now, if you look at the concentration of H3O+, well, you see that the H3O+ is a product. So we definitely, because we're adding more of this, we are going to produce more H3O. So we are going to increase the amount of H3O. And so that would have to increase. And so your H3O concentration increases, but your Kw remains the same. And so the answer is C. Consider the ionization reactions 1 and 2. And then they give us these ionization reactions over here. Okay, so they just want us to fill in the rest. Now, this is actually pretty easy because look here. If you just look at these two and you look at that, we can see that this water molecule gained 1 hydrogen. Can you see that? It gained 1 hydrogen. Where did it get that hydrogen from? Well, it would have gotten it from this one over here. So this one gave 1 of its hydrogens. And so over here, it would simply be HPO4 and then -2. Okay? It doesn't give away both of these hydrogens, it just gave away 1 of them to become HPO4 -2. So X is definitely going to be HPO4 -2, so the answer cannot be that one. Oh my goodness, so it could be any one of these. Okay, then they take X and they put it over here, so HPO4 -2. Now let's see what happens. This water molecule gains another hydrogen to become H3O. So where did this water molecule get its hydrogen? Well, it's getting it from this one over here. So that means that this molecule is now giving away its other hydrogen so that this one can become H3O. And so this one would now become PO4 -3. And so A would have to be the answer. An electrochemical cell was set up using a mercury half cell, so Hg and Hg2+, and another half cell under standard conditions. Which one of the following half cells, when connected to this one, will result in the highest cell potential? Okay, we definitely need to go get our table. Okay, so here we have our table. Now, remember, they want us to connect, they want us to use Hg and the Hg half cell over there. And then they want to know if we connect that one to any one of these, which one will give us the greatest cell potential? Now, cell potential is like your voltage, okay? So let's just go highlight all of those. Aluminium, there's the zinc one, there it is, and cobalt. Okay, now, remember, I've explained this to you before with galvanic cells, how to work out which one's the cathode, which one's the anode. And remember, we're just looking for the best reducing agent. So it says here increasing strength of reducing agent. So you follow this arrow and you choose the highest one on the right. There it is. By the way, I'm using table 4B. That's what most schools in South Africa use, not table. So I'm using table 4B, not 4A. But you can follow the same idea. You're finding the best one with that arrow, and then with this arrow, you're looking for the increasing or the best oxidizing agent. And so the lowest one down on the left would be that one. Okay, so that would give you the ultimate best scenario, where you've got the strongest reducing agent and you've got the strongest oxidizing agent. That'll give you the biggest cell potential. I'll show you, because if you had to go calculate this, E cell, the formula E cathode minus E anode, okay? Now, I've showed you this before, but this reaction down here at the bottom, when it goes Hg 2 plus 2 electrons goes to Hg, that is a a redox reaction. That's a reduction reaction. And so reduction always happens at your cathode. Reduction happens at your cathode. And then when the reaction goes from right to left like that, so if it goes aluminium turns into aluminium 3 plus 3 electrons, that is a oxidation reaction, and that happens at your anode. Okay? So we're going to take the Hg value, which is 0.85, minus this one's value. Now look at this, guys. It's negative 1.66. So that's going to end up becoming a plus 1.66. If it was this one, it would only become a plus 0.76. If it was this one, it would only become plus 0.28. And so the best, or the highest voltage that you are going to get, or the highest cell potential, is going to be when you connect the Hg with the aluminium. So the answer is A. The following reaction takes place in an electrochemical cell. Which of the following is correct for this cell? So what I want us to do is I want us to focus in our attentions on A and B. So we should know from electrochemistry that if it is a galvanic cell, that is when everything is spontaneous, okay? That's the one where you have like 2 half cells and you've got a spontaneous, and if you had to work out the value of the cell potential, it's always bigger than 0. It's always bigger than 0. If you need a power source, then that is electrolytic, and that is when it's non-spontaneous, and that is when your E cell is smaller than 0. It's when it's negative, okay? So let's go get our table, and let's try to see if we can figure out the E cell value, and from that we will be able to make some conclusions over here. Before we go to our table, though, we need to know what to go look for in our table. So we know that this is just pure copper, that's pure Cl2. So there's the oxidation numbers there are just 0. But we need to work out the oxidation numbers here. For example, you need to know what copper's oxidation number is. Maybe it's a 3, then you would go look for a plus 3 copper on your table, but maybe it's a plus 2. So we need to work out the oxidation numbers here. So let's quickly get our periodic table. Okay, now with working out oxidation numbers, if you look at Cl is over here, so it's got a valency of -1. Remember, it goes 1, 2, 3, 4, and then -3, -2, and then -1. So I'm going to put a little -1 over there. Now, we're going to set up an equation, okay? So we're going to say that copper is X, because we don't know what copper is. You can't find it on the periodic table because it's a transition metal, so it's got different, it can have different oxidation numbers. So we're going to say, depending on what molecule it's in. So we're going to say X plus. Now, there are 2 chlorines, and each one is a -1. And then we're going to make that equal to 0. The reason I make it equal to 0 is that this overall molecule has an oxidation number of 0, because if it had a charge, they would have had like a +2 over here or something like that. Okay, so if you had to work out X, you're going to end up with a 2. Okay, so that's a +2. So the copper is going from +2 to 0, and the chlorine is going from -1 to 0. Okay, so let's go get our table 4B now. I use table 4B. Most schools in South Africa use table 4B. There's only some that use 4A. Okay, so here we have the table. Now, what you got to do is just look out for, you see what we have here is Cu plus 2, and on this side you have Cu. So some learners get confused with, should we use this one over here, or should we maybe use this one over here? And it's very easy. All you do is you look at what you have. So we've got Cu plus 2 and Cu with no charge. So we will use this one over here, okay? And then for the Cl, we've got a Cl with a negative, and then we've got a Cl2. So that's down here at the bottom. A Cl2 with a negative and a Cl. Okay, now what we're going to do is you got to look at what we have. So what do we have at the start? We have Cu plus 2, okay? So that means our reaction is going to start at Cu plus 2, and it's going to go that way, Okay, and then if you look at the Cl, we've got a Cl minus 1, and then it becomes a Cl2. So that means we're going to start with a Cl minus 1, and then it's going to become a Cl2. So those are the directions of our reactions, okay? Now, from previous lessons and however your teachers explained, or if you've watched some of my lessons, we should know that when it's going from left to right, like that, then it is a reaction. And we know that that always happens at a cathode. Okay, when it goes from right to left, like what we have here, then it is called an anode. Well, sorry, first of all, we say that that is called oxidation, and we know that oxidation takes place at an anode. We now know that there's this formula to calculate the EMF of the battery if it was a galvanic cell, and that would be cathode minus anode. Okay, so if you look at the cathode value, it's 0.34, and if you look at the anode value, it's 1.36. If you go and calculate this, you're going to get a negative answer. Now, remember what we said. If your answer is negative, it means non-spontaneous, and that means it needs a power source because it's an electrolytic cell, okay? And so the answer would be B. If it was a positive answer, that means spontaneous, and then you would have chosen A as your answer. But for this one, it'll be B. Okay, so here we have a table with a whole bunch of organic molecules. And so this question will carry on the next slide. We've actually got quite a few questions. We've got this one, this one, this one, and this one. So it's a lot of questions. So it says, write down the letter that represents a ketone. Okay, so a ketone is a molecule like this, for example, which has a whole bunch of hydrogen. And then you would have like a double bond oxygen over here. Now, what's important for it to be a ketone, the double bond oxygen on the carbon like that must be in between two other carbons. Okay, it mustn't be in between a carbon and a hydrogen. It must be in between two carbons. Okay, so let's see. Okay, so it's definitely not that one. It's not that one. It's not that one because that's an alkene. It could be that one. Let's have a look. Although you see this oxygen is on the side. When it's on the side, then it is normally, well done, an aldehyde. Whereas here we have an oxygen somewhere in the middle. So it's actually going to be E, because we should know that when you name a ketone, it always ends in the word O-N-E. So that's also in the word ketone. Okay, so write down the letter. It is E. Which substance has the general formula CnH2n-2? Now you should know from just your general theory on organic chemistry that we've got three types of hydrocarbons. We've got alkanes, alkenes, and alkynes. Okay, now alkanes have the general formula CnH2n plus 2, alkenes CnH2n, and alkynes like that. So we know that this then is an alkyne, which is something that has a triple bond. And in the word alkyne, we can also see YNE. So these are substances that end in the word YNE, and so this one would be F. This question says, is an isomer of 2-methyl but 2-ene? Okay, so let's talk about isomers. Okay, so isomers have the same amount of each atom, okay, but the atoms are structurally arranged differently. Okay, I know that the English there wasn't the best, but you know what I'm trying to say. Structurally, the atoms are arranged differently. So, for example, one example is something like this, which is butane. So if you had to go count all the carbons and hydrogens, we would have 4 carbons and 10 hydrogens, okay? But if you instead had to look at this molecule, which if you had to go count everything, it would also have 4 carbons and 10 hydrogens. However, you see that we've arranged it differently. And so what I was trying to say is that isomers have the same amount of each atom. So that's what we can see here. Same amount of carbons and same amount of hydrogens, but the atoms are structurally arranged differently. And remember, we get 3 different types of isomers: chain, functional, and positional. Okay, so what we are doing here, they're saying it is an isomer of 2-methyl butene. So let's quickly go draw that. So it's a 4-carbon molecule. Well, it's got 4 carbons in the main chain because of the BUT. On carbon number 2, there is a double bond over there. And then on carbon number 2, there's also a methyl branch, which is a 1-carbon branch. Okay, now I'm going to go fill in hydrogens everywhere else. Okay, so let's go count all of the carbons. So there is 1, 2, 3, 4, 5 carbons. Okay, so that's going to be 5 carbons. Then let's see how many hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 hydrogens. And that's it. Okay, so we're looking for a molecule that's going to have 5 carbons and 10 hydrogens. So if we come here to pent2-ene, we know that pent is 5. So pent is 5. And then on carbon 2, there's a double bond. There it is. Now we just go put hydrogen everywhere else. Remember that each carbon must only be surrounded by 4 things. So over here, we've already got 4 things. You see 1, 2, 3, 4. Okay, there we go. And I don't add a hydrogen here because there's already 4 bonds around that carbon. So if we go count 1, 2, 3, 4, 5 carbons, that looks good. Let's count the hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. Exactly the same as that. And so the isomer will be compound C. So we'll say C over there. This one says, write down the letter that represents a compound that has the same molecular formula as ethyl ethanoate. Well, this is another isomer question because isomers have the same molecular formula because they have the same amount of everything. For example, this one over here would be C5H10, but then this one that we had earlier would also be C5H10. So isomers have the same molecular formula, but they look different. So we're going to go quickly check out ethyl ethanoate. Okay, so ethyl ethanoate, that is an ester. Now remember, with an ester, the first part is the alcohol part. So let's go draw that in, CC, and then O like that. And then there's the carboxylic acid part, which is the ethanoate. So we'll put that over there. Okay, and then all of the rest is hydrogen. So if we had to go count all the carbons and everything, we'd get 1, 2, 3, 4. So 4 carbon. The hydrogens, there would be 1, 2, 3, 4, 5, 6, 7, 8. And then the oxygens, there would be 2. Think about this carefully. What other molecules do we know that have 2 oxygens in them? It's not alcohols, because they have an OH. It's not aldehydes, they have an oxygen. It's not ketones, they have an oxygen. It's carboxylic acids. Carboxylic acids have 2 oxygens in them. See there? So we have to go find a carboxylic acid in this table. Now, a carboxylic acid always has that Cu part. Look at that. You know how a carboxylic acid has that? Let me just show you again. See how it's got that C double oxygen hydrogen part there? So that's probably the answer, but let's just make sure that this has 4 carbons. 1, 2, 3, 4. Perfect. So this would be an isomer of ethyl ethanoate. Remember that, guys. Carboxylic acids and esters are isomers of each other. So if we had to go look at the molecular formula of this one, in case you're interested, there's 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and then 2 oxygens. Look at that, it's perfect. Okay, these questions carry on. It says write down the IUPAC. Okay, so that's the naming of compound A. Okay, so the first step, remember naming. First step is, remember, I like to break naming up into 3 main parts. And the first part, which is this part, is what is the length of the longest carbon chain? So for example, 1, 2, 3, well, let's go draw it out first, should we? So let's expand it. So it's CH3, then there's a carbon. Now attached to that carbon is a Br, and attached is a CH3. So we're going to put a CH3. Okay. Then there's a CH2. Then there is a carbon, just a random carbon, which has a CH3 attached to it. Or we can go down or up. It's also got a hydrogen attached to it. Okay, and then we get to another carbon, which has a CH3 and a hydrogen, and then there's a CH3. Okay, so the first step is to find the longest continuous chain. So that'll just be 1, 2, 3, 4, 5, 6. Okay, yes, some of you might say 1, 2, 3, 4, 5, 6, for example, or some of you might say 1, 2, 3, 4, 5, 6. That's all fine. You're not going to get more than 6 though. So that we're going to call hex, because 6 means hex. The next step is to try to figure out, what is this molecule? Like, is it an alcohol, ketone, aldehyde, carboxylic acid, alkene, alkane? What is it? Well, you see it's just got a whole bunch of carbons and hydrogens, but then there is a halogen over here. So this is a halo alkane. Now, when you name a halo alkane, you don't put like hex halo or something like that. No, you just put ANE at the end. Okay? And then this part is the branches. Okay. So we are going to look at all the branches now. So if this is the main chain, then the branches are all the parts that are going to stick out. So it's going to be that part, this part, and this part. Wow. Okay. So there's quite a few branches there. Now you want to name this molecule from the side that gives us the lowest branch numbers. Some of you might be saying, Kevin, don't we name it from the side closest to the BR because it's a haloalkane? And this is the part of organic chemistry of grade 12 that a lot of teachers don't mention. Normally, if it was like an alcohol, aldehyde, ketone, alkene, alkyne, anything like those that have functional groups, you normally name it from the side that is closest to the functional group. But with a haloalkane, you don't necessarily name it from the side that's closest to the functional group. You name it just like you would name a normal alkane, where you try and make the branch numbers as low as possible. It's weird, right? But that's what happens with haloalkanes. You don't name it from the side closest to the functional group. You name it from the side where you get the lowest branch numbers. So the haloalkanes are like, they didn't really make it in life, okay? They like failed functional groups. They're not that powerful. So we ignore the functional group part and we just treat it as a normal branch. Okay, so check this out. If we name it from the left, where would your branches be? Well, there would be a branch on carbon number 2, which is this one and this one. There would be a branch on carbon number 4, and there would be a branch on carbon number 5. Okay? So that's 2, 4, and 5. Just remember those numbers, 2, 4, and 5. If we name it from the side that is on the right-hand side, then we would get a branch on carbon number 2, carbon number 3, and carbon number 5. And so we will choose that because that gives us the lower numbers. So we are going to label this molecule from the right-hand side. So on carbon number 2, on carbon number 3, and on carbon number 5, we're going to have methyl branches. And then on carbon number 5, again, we have a bromo. Now, the rule of our UPAC says it must be alphabetical. So B comes first, so we're going to start with that one. So we're going to say 5 bromo. Then we're going to say 2, 3, 5. And then we're not just going to say methyl. We're going to say trimethyl because there's 3 of them. If it was 2, you would say di. If it's 3, you say tri. And so that would be the name of this molecule. And so even on the memo, they made the classic mistake where they named it from this side because they think you must name it from a side that's closest to the functional group. That is correct if it was an alcohol, alkene, alkyne, any of those other molecules. But with haloalkanes, it is not true, okay? I'll even show you, so it's not just me saying this. There is also certain textbooks that even mention this. I'll show you this textbook. Hold on. All right, so here we have another textbook. Now have a look at the part that I've highlighted. It says that you must number it from the side that is nearest to the first substituent, which means branch, irrespective if it is a halogen or an alkyl group, okay? Ignore the part with double and triple bond. Then in brackets here, when haloalkanes are named, the halogen atom is regarded the same as any other substituent and does not enjoy preference above the others. So you don't treat haloalkanes like normal functional groups. They are the only ones that have this weird thing. So please keep that in mind. A lot of teachers don't know this. Okay? Now this question says, what is the structural formula of compound F? So compound F, we're just going to go draw it out. Okay, so the way I like to draw it, it's very easy. You just go to this part here. So that's pent. So we make 5 carbons. 1, 2, 3, 4, and 5. Okay, that part's done. On carbon number 2, triple bond, because that's what YNE is. That's a triple bond. So you can label this as carbon 2, or you can do that as carbon 2. It doesn't matter. So we put a triple bond. Okay, that's done. Then on carbon number 4, so if that's number 2, then this is number 4, there is going to be a dimethyl. That means there's going to be 2 methyls. So there's going to be a methyl going up and a methyl going down like that. Okay, and now we are just going to go fill in hydrogen everywhere else, making sure that each carbon is always surrounded by no more than 4 bonds. Okay, so here you won't add anything because this carbon is already surrounded by 4, and this carbon is already surrounded by 4. Okay, and so that would be your answer. And as I said, you could also do it the other way around. Okay, so yours might be the other way around. For compound D, okay, which is going to be an aldehyde because it's got an oxygen on the side, could even be a alcohol, but we'll check. Write down the homologous series. So let's go draw it out to make sure what it is. So it's got a CH3, see that? Then it's got a CH2, okay, so CH2. Then it's got another CH2. Then it's got a carbon with a hydrogen and an oxygen. You might say, yeah, but Kevin, how do you know that it's not this? It can't be that, because then look here, there's nothing here and there's nothing here. And so this thing would be empty, okay? And you can't put like a double bond and a triple bond because then this one's going to have problems. So the only way that this would work is that the hydrogen is here, for example, and then you've got the oxygen, but the oxygen is a double bond. Now you could also do that like this, for example. But we're definitely going to have a double bonded oxygen because otherwise things just aren't going to work out over here. Let me show you that again. Some learners would say maybe the O and the H is together. Fine, let's put them together. But then you have a carbon here that only has 2 bonds. But then you might say, yeah, but Kevin, then we can just put a triple bond. But then this one has too many. And so the only way that this would work is that the hydrogen is alone, and then you've got the double bond oxygen. We see this double bond oxygen with aldehydes, ketones, carboxylic acids. Now, if you look at this, we've got a double bond oxygen, just like a ketone, but this double bond oxygen is on the side. Can you see that this carbon is in between a carbon and a hydrogen? So it's not a ketone. This is an aldehyde because the double bond oxygen is on the side. Okay, and then it says, what is the name of its functional group? The functional group is the part of the molecule that gives it its special property, and so that's this area over here. Specifically, it is that and that. So we have to show that one of these parts is a hydrogen. Okay, now if they were just talking about that part over there, then you call it a carbonyl. But that's not what they're talking about. They're talking about its whole functional group, which is this. Oh, there's a little line there. This part over here. Now, it's actually quite an interesting one. It's called a 4-mil. You're probably never going to see a question like that. I've never really seen it, to be honest. But that part there is called a formal group. Okay, now it says draw or give the structural formula, which means draw, of its functional isomer. Okay, so we need to understand the following. In grade 12, we get isomers, right, which we spoke about earlier. And we get 3 types, chain, position, and functional. Now, if you look at functional, okay, let's take functional and talk about that a little bit further. These are isomers with different functional groups. Now remember, a functional group is the part of the molecule that makes it unique, like an alcohol, aldehyde, ketone, carboxylic acid, ester, alkene, alkyne. Okay? So if a molecule has a different functional group, then it means it's a totally different molecule. So functional isomers are different homologous series. So like the one might be an alcohol and the other one might be an alkene or an aldehyde or a carboxylic acid. Now, let me quickly make this easy for you. In grade 12, there are only two functional, or like two types of functional isomers, okay? I'll show you both. The first one is with an ester and a carboxylic acid. So let me show you an ester quickly. I'll show you a 5 carbon, no, let's go with the 3 carbon ester. Okay, so that is an ester with 3 carbons, right? Then I'm going to draw a carboxylic acid with 3 carbons. So go ahead quickly and check how many carbons there are in both molecules, how many hydrogens, and how many oxygens. You will see that it is exactly the same. There are 3 carbons, 6 hydrogens, and 2 oxygens. These are functional isomers because this is an ester, this is a carboxylic acid. Their functional group is completely different. The other one that we need to know for grade 12 is aldehydes and ketones. It's only these two, okay? So let me draw you a 3 carbon aldehyde. Double bond oxygen always on the side if it's an aldehyde. And then with a ketone, the double bond oxygen is always on a carbon that is in between 2 other carbons. Okay? If you had to now go count all the carbons, all the hydrogens, and all the oxygens, you would see that it is exactly the same in these 2 molecules. In both molecules, you're going to have 3 carbons, 6 hydrogens, and 1 oxygen. So those are functional isomers once again. We can see the functional group is totally different, but they have the same amount of each thing. So remember this one for grade 12 and remember this one for grade 12. So here they say, take this aldehyde, which we had, and give its structural formula for the isomer. So we just learned that the isomer of an aldehyde, or the functional isomer of an aldehyde, is a ketone. So all I'm going to do now is I'm just going to see how many carbons this thing has. 4. And I'm just going to go make a 4 carbon ketone, however you want. We know that with a ketone, the double bond oxygen is somewhere in the middle. So like maybe there. Okay, and then just go fill in hydrogens wherever we have to. Don't put a hydrogen here because then this carbon would have more than 4 bonds. And that's it. That is, and don't put this carbon double bond oxygen on carbon number 1 or on carbon number 4 because then it's an aldehyde, because then the double bond oxygen is on the side. But for it to be a ketone, the double bond oxygen has to be in between 2 other carbons. Okay, and so there's your answer for this one over here. Okay, this one says for compound G, which is butane, let's quickly draw that out. It's just a 4 carbon alkane. It's basic as you get. Kevin, it's not basic, it's acidic. Yeah, you know what I'm talking about, guys. I meant like it's basic as in it's easy. For compound G, write down the IUPAC name of its chain isomer. Okay, so what is a chain isomer? Well, a chain, or first of all, what is an isomer? Well, we've spoken about that quite a bit. So an isomer has the same amount of carbons and hydrogens, for example, as this one. But to have a chain isomer, you have to take this chain length, which is 4, and make it different. So what we can do is let's make it 3 carbons, and then let's put the other carbon over there. Don't put the other carbon over there, because that's still going to be 4 carbons long then. And don't put it over there, because that's still going to be 4 carbons long. Put it over there. Then it's not, then you can only have 3 carbons in the main chain. Then just go fill in hydrogens everywhere else. And this is what a chain isomer is. It's the same number of carbon and hydrogen in both molecules. But here we have 4 carbons in the main chain. Okay. Here we have 3. And then we just add a branch over there. Okay. So that is what it would look like. But now we need to give the name. So the main carbon chain, how many carbons are there? 3. So that's prop. So we're going to say prop. What type of molecule is this? You have 9 options. Ester, carboxylic acid, alcohol, alkene, alkyne, you know, all of those. Well, this is just an alkane. So it's still an alkane. Okay, so it's definitely not a functional isomer because it's still an alkane in both. However, on carbon number 2, we have a methyl branch. And there we go. That would be the name. This question says a balanced equation for the complete combustion. Okay, you need to understand that combustion is when you take a certain material, you react it with oxygen, you produce carbon dioxide, and water. Okay, that is what combustion is. Whether the starting material is an alkane, alcohol, alkene, it doesn't matter. So what we're going to do is, and they're saying for compound G, remember that. So butane, if you go, they want us to use molecular formula. Okay, so if you look at butane, it's got 4 carbons, and it's got, if you go count, it's got 10 hydrogens. Okay, then you're just going to say plus oxygen, which is diatomic, so it's O2. Then you're just going to say CO2 plus water. Now to balance this thing, always balance the carbon first, then the hydrogen, then the oxygen, in that order specifically. Trust me. So we start with the carbon. On this side there are 4 carbons, so we'll put a 4 over there. Okay, look at the hydrogen next. On this side there are 10, and on this side there's 2. So we'll put a 5 over here, because 5 times 2 is 10. Now do the oxygen. On this side there's 2. On this side there is 4 times 2, which is 8. 5 times, that's just a 1. It's just a little 1 over there. So 5 times 1 is 5. So there are 13 oxygens on the right, and there are only 2 on the left. So what you do is you multiply this side by 13 over 2. Because if you say 13 over 2 multiplied by 2, that's 13, right? But now we just have a little bit of a problem, and that is we're not allowed to leave it as a fraction. So what we do is we get rid of this denominator by multiplying everything by 2. So we put a 2 there. This will just become a 13. This will then become an 8. And this will become a 10. And there we go. Learners investigate factors which influence the boiling points of organic compounds. The boiling points of some organic compounds are shown below. Okay, so we've got some organic compounds: propane, butane, pentane, methylbutane, ethanol, and ethanol. First question, define the term boiling point. No, you cannot say the temperature when a liquid turns into a gas. However, keep that in mind. Liquid, gas. It is the temperature when a liquid goes to a gas, but the proper definition is the following. Okay, so what is it actually? Well, if you take a pot of water, okay, you take a pot of water and you start heating that water up. That water is going to start giving off a little bit of steam. You can see the steam that gets released, okay? It doesn't mean the water's boiling necessarily. But what's happening is that this water is starting to create gas in this area. Now that gas has a certain pressure, which we like to call vapor pressure. Okay? Now, there is already surrounding gas due to the world that we live in. The world we live in has air, and there's vapor, and there's an atmosphere. Okay? That was already there. This is the atmosphere. Now, when the vapor pressure increases and increases and increases, and it eventually becomes the same as the atmospheric pressure, bubbling starts occurring, and that is boiling point. So, boiling point is the temperature at which the vapor pressure of a substance equals atmospheric pressure. Okay, it is the temperature at which the vapor pressure of a substance equals atmospheric pressure. Let's move on. So, remember, there will be quite a few questions coming up, by the way. There's going to be there, and there, and there. The boiling points of compounds A, B, and C. Okay, so propane, butane, and pentane are compared. How do the boiling points vary from compound A to C? Well, that's pretty easy. Check the boiling points. What is happening to them? They are increasing. So we can just say increases. Okay, now explain the answer. Just say, I saw it in the table. Okay, no, you can't say that for 3 marks. But, so it's a pretty weird question, right? Like, explain the answer. Well, it's because we saw it. But I guess what they mean is, explain why the boiling point increases for those molecules. Okay, so we've spoken about this many, many, many times, but let's just have a look. So if we have propane, it's a 3-carbon molecule. So if you put another propane molecule next to it, you can imagine that there are intermolecular forces in between, right? Of course, there's hydrogens everywhere, but I'm not going to go draw those all in. But remember, that's what propane looks like, okay? And there's all these intermolecular forces between them. If you then look at butane, it's a 4-carbon molecule, okay? So it's a little bit longer. And then that would also have intermolecular forces. If you look at pentane, it's a 5-carbon molecule. And then once again, intermolecular forces in between. And so remember that these are alkanes. Alkanes have London force intermolecular forces. And what do we know about London forces? We know that London forces become stronger when the molecules become longer. Why? Because London forces, there's many different ways you could say this, but one of them is that you are increasing the surface area. So you see, for example, here we've only got space for London forces over there, but here we have a longer space or more area for the London forces to act, and here we have even more area for the London forces to act. Another word you can use instead of surface area is you could use molecular mass. That's another one we use with London forces. Okay, so for 3 marks, how are we going to write this down? So you could say something like, from A to C, the surface area increases. You could then say that London forces increase with increased surface area. Okay, and then you can therefore say the conclusion, which is therefore more energy needed to overcome the stronger forces of attraction. The next one says that the boiling points of compounds B, C, and D are compared. Is this a fair comparison? B, C, and D. And then it says choose from yes or no and then give a reason. Okay, well, it was definitely a fair comparison to compare all of these because they were all the same kind of like shape. For example, they were all in a straight line and they were just increasing the length. But now when you look at methyl butane, that is a butane molecule which has a methyl on one of these 2 carbons. It can't be on the end carbon because then it would actually just make the chain longer and it would actually just become pentane. So methyl butane is the methyls on one of these carbons. It doesn't matter which one you choose. I'm actually going to go down like that. So this is methyl butane. You might even call it 2-methyl butane. Okay, so that's 2-methyl butane. And then they're comparing that one with butane and pentane. Okay, so butane with obviously all the hydrogens, and then pentane. So this is definitely not a good comparison, but let me just try explain why the previous one was okay. The previous one we looked at A, B, and C, which was propane compared with butane, compared with pentane. So the only variable that was changing was the length. That is the only variable, okay? But if you look at these ones, you've got a 4-carbon and a 4-carbon and a 5-carbon. So they've got different lengths, okay, like they did over here. But then they also have a straight and a straight, and then they also have a branch. So they're changing 2 variables. They're changing the length, but then they're also making some of them have branches and some of them not have branches. So they're doing multiple variables, and that's not right. You're only supposed to change 1 variable in an experiment at a time. So we are definitely going to say no. More than 1 independent variable is being changed. Okay, so when they compared the propane, butane, and pentane, they were just increasing. They were changing 1 variable, the length. Okay, which is also the length, but that's also like changing the mass. It's the same kind of thing. But here in this one, they're changing the length of the chain, but then they're also having some of the molecules have branches and then some of them don't have branches. So that's another variable. So you can't really make a conclusion as to why there is a difference in boiling point, for example, between this one and this one, or this one and this one. Is it because of a longer chain length, or is it because of the branches? You see how it becomes a bit difficult to say. So this one says the boiling points of compound E and F are compared. So state the independent variable. Okay, so if you look at ethanol, which is an alcohol molecule, okay, and then ethanol, which is an aldehyde molecule, also with 2 carbons. So let's put the double bond oxygen. Remember, with aldehyde, the double bond oxygen is always on the side. Okay, so this is a fair comparison. I like this one. They've got the same carbon length, so the same chain length, but what they're changing is here they're using an alcohol, and here they're using an aldehyde. So what are they changing? They're changing the functional group. That is what they are changing. Then they say here, write down the name of the strongest van der Waals force in compound F. Okay, this is F, and this is E. So remember that your van der Waals forces are things like, it's your London forces or dipole-dipole. Okay, those are your van der Waals forces. Now, if you think about a molecule of ethanol, if you want to look at intermolecular forces, you're going to have to draw a second one, because intermolecular forces take place in between the molecules and not inside a molecule. So it's not these forces over here. Those are like covalent, ionic, metallic. What we're talking about is the intermolecular forces, which is between them. Okay, so we know that an area like this, which is just carbon and hydrogen, that's typically just your London forces, right? You know, like how the forces we had between propane molecules, for example. That's just your London forces, okay? Because the carbon-hydrogen area is non-polar. However, we've got this this area here, okay? For example, this area over here. If you look at your table of electronegativities, you'll see that oxygen and carbon have differing electronegativities, and so what that does is it creates this area, causes this area, to become, whoopsie, I don't know what happened there. It causes this area to become polar. This is a nice polar area, and this is a polar area as well. Now, when you put two polar areas next to each other, they are going to attract each other, because this will be very negative, this would be very positive, for example. So there would be an attraction there. And when it's a polar and a polar, we call that a dipole force. So that is the name of the strongest one, much stronger than a London force. So you're going to say dipole. So this question says, which compound, D or E, has a higher vapor pressure? Okay, let's talk about vapor pressure quickly. Let's say we have two scenarios. Let's say we have a molecule with, or let's say molecules with weak intermolecular forces. And then here we have molecules with strong intermolecular forces. Okay, so here are the molecules here. Okay, and then here are the molecules here. Now, if these molecules have weak intermolecular forces, then it means that there is not a lot of strength that is holding these molecules together. Okay, so these molecules can actually move wherever they want. They can move further away from each other. Okay, because there's not a lot of force holding them together. So, okay, now if you look at these ones have a much stronger intermolecular force between them. So it's going to keep them closer together. Okay, so let's keep those ones like that. So, which ones, A or B, would you expect to be more... Okay, let's not use A and B, because then you might think I'm talking about this A and B. Let's say W, or let's say X and Y. Hello, mathematics. X and Y. So in which one, and then we can just solve this simultaneously. Okay, that was a joke. So in which scenario would you expect the molecules to be more in the gas phase compared to in the liquid phase? Remember, liquid molecules are closer together than gas molecules. Okay, so this one here on the left would be more gas, because the molecules are further apart, because there's less intermolecular forces holding them together. And then here we would have more of a liquidy type of scenario. Okay, so vapor pressure, that's gas. Vapor, it's gas. So if you have a room that's got lots of gas in it, then it's going to have a high vapor pressure. If you have a room that's got very low or small amounts of gas, then it's a low vapor pressure. So we would expect this one to have a high vapor pressure because there's more gas moving around, exerting pressure. Here we would have a lower vapor pressure. So what we can say then is that when you have weak intermolecular forces, you have a high vapor pressure. When you have strong intermolecular forces, you have a low vapor pressure. Another question I have for you is, which molecules, these ones or these ones, would it be easier to turn into a gas? Well, obviously it'll be easier to turn this into a gas because these molecules don't really have much forces in between them, so it's easy to turn them into a gas. So this would have a low boiling point because you don't need much energy to boil them, so the temperature can be low. These ones would need a very high boiling point, or higher, because you need more energy to try separate them into the gas phase because they're holding on to each other because of the stronger intermolecular forces. So another conclusion we can make is when you have a low boiling point, you have a high vapor pressure. When you have a high boiling point, you have a low vapor pressure. So if you just look at these, so if they wanted us to compare D and E, so if you just look at the boiling point, we can see that ethanol has a high boiling point. So that means the molecules are difficult to separate because you need a much higher temperature or more energy to separate them. Whereas here you've got a lower temperature, so it means it's easier to separate them into the gas phase or to cause them to boil. So this molecule is lower boiling point, so it's going to have a higher vapor pressure. So it says here, which compound D or E has a higher vapor pressure? It's going to be compound D. And the reason is that it has a lower boiling point. It has a lower boiling point. Okay, so these questions are going to carry on. Here's the first part and the second part. Okay, so it says study the following equations for organic reactions number 1 and number 2. The compounds P and Q are organic and T is inorganic. Okay, for reaction number 1, write down the type. Type could be like combustion, esterification, elimination, addition, substitution, things like that. So you need to understand your reactions really well. You need to understand, for example, that this is a haloalkane. So let's write that down. Haloalkane. Now you need to understand what you can do with haloalkanes. If you've ever seen my videos on the diagrams where I show the different reactions, haloalkane is usually chilling over here on that diagram. Haloalkane. And so you can take a haloalkane and you can convert it to an alkene, but you could also convert a haloalkane into an alcohol, okay? And each of those require different conditions. So what we've got here is, I've made videos on this in the past and we've spoken about this a lot. When you use NaOH, sometimes they use KOH, which is a strong base, there is a big difference if you use concentrated or if you use diluted, for example. You could use concentrated or dilute. If you use dilute, then it goes this way. Okay, that's dilute. If you use concentrated, then it goes this way. So when you're going from a haloalkane to an alkene. So this is obviously an alkene over here. Okay? You now have to think about if this is elimination, addition, substitution, or what it could be. So if you're going from a haloalkane, okay, and then you are forming an alkene, which has a double bond. The only way you could do that is if you take some of these atoms, maybe like this one, and another one, if you take those off. So you are doing elimination. This is elimination. Okay, so with organic reactions, you need to understand, if you have a this, then it can become a that. And if you have a that, then it can become a that. Okay, now the next one says, what is the IUPAC name of compound P? Okay, so let's try to figure out what's going on here. We know that we're definitely going to lose a halogen because we're forming an alkene. And let's just quickly draw this out so we can quickly use Zaitsev's rule. So we have CH3, and then there's an H over here, which is this one, and then there's a Br, and then there's another H, and then there's a CH3. Okay, so what happens is that when you use elimination, you're definitely going to get rid of this. But now the big question is, do we take another hydrogen off of this carbon, or do we take another one off of that carbon? And this is where we use the riddle that I hope you've maybe heard me say is the rich get rich, or the richer get richer, whatever, and the poorer get poorer. When I say this, I'm talking about hydrogen. So what we do is we look at, so you don't look at this carbon. That carbon's done. We've already taken something. You look at this carbon and you look at this carbon. And this carbon has how many hydrogens? It's got 1, 2, 3. Okay? If you look at this carbon, how many hydrogens does it have? It's only got 1. So when we are using elimination, we're not looking at this part. We're looking at this part. The poorer get poorer. So who was the poorest in hydrogen? Well, not this one. This one already had 3. This one had 1. So this is the poor one. Okay? Now it says that the poorer are going to get even poorer. So we're going to lose this hydrogen over here. Okay? So you're going to take that hydrogen away, and you're going to take that bromine away, and in its place, because now these carbons only have 3 bonds, you are going to put a double bond. That's how you produce the alkene. Now they want the name of this molecule, so we are going to name it from the side that is closest to the double bond. But if you look carefully, the double bond is in the middle. So the next best thing is that we're going to name it from the left-hand side so that this branch can have the lowest number possible. So to name it, you're going to see how many carbons are in the main chain. That is going to be 4. So you're going to say but. Then on the double bond is on carbon number 2. So you're going to go like that. And then on carbon number 2, we also have a branch, a 1-carbon branch. That's a methyl. And there we go. 2-methyl, but 2-ene. If you called it 2-methyl, but 1-ene, then you didn't do this part. You didn't do the poorer get poorer part properly. This next one says, what is the name or formula of compound T? Okay, so the name or formula of compound T. So let's try to figure out what's going on here. So what we know is that the alkene is over here. Okay. We also know that this Br is going to join this Na, and that's where the NaBr is going to come from. We also then realize that this OH is going to be floating around by itself, so it will be joined by this other. Remember, there was a hydrogen over here, the poor one. Well, that hydrogen will just get knocked off, and it will just go and join this OH to become water. Let me explain that again. So this Br is going to go join up with the Na to become NaBr. This H that we knocked off, this one over here, or you can think about it as that one over there, that's just going to go and join, that OH over there, and then they'll just become water over here. Okay, this one says, for reaction number 2, write down 2 reaction conditions needed. Okay, so this is you need to identify whenever you see the C double bond, or C double oxygen hydrogen. I always say C double bond. It's C double oxygen hydrogen. That is a carboxylic acid. So I'll show it to you. There's the CO and then another OH. You see there's that COOH. That is a carboxylic acid. Now we know that the only reactions that carboxylic acids do in grade 12 is the reaction with alcohols to produce esters. That produces an ester. Okay? And that is to produce esters. Okay, so the reaction conditions for esterification is we've got to use a catalyst. We know there's that sulfuric acid catalyst. Okay, so we'll say sulfuric acid catalyst. Oh, and it must be concentrated. Let's just write that down. That's important. Concentrated sulfuric acid catalyst. That's one. The second one is that we use heat. Okay, so those are the 2 reaction conditions that we use for esterification. The next one says, what is the structural formula of compound Q? Okay, so we know that to make an ester, you take a carboxylic acid, which we have there, and you react it with an alcohol. Okay, so this is definitely an alcohol, but we don't know much about it. However, we can see that the product is butyl ethanoate. Now remember, when you name a ester, the first part is always the alcohol, and the second part is the carboxylic. So this carboxylic is eth, which is 2 carbons, but we can see that over there. The alcohol part is a 4-carbon because it's BUT. So this is a 4-carbon alcohol. So just go draw the most basic 4-carbon alcohol that you can. So just give it 4 carbons. Add an OH. Let me add the OH in a better place, actually. I'm going to add the OH here. And then just put hydrogen everywhere else. And that's it. So let's just finish that up. And there we go. With this question, I will split the different parts up onto different screens. But just in case you want to look at all the questions, here they are. Okay, so it says that the cracking of a long chain hydrocarbon, which is C10H22, which is an alkane, in case we need that, I'm not too sure if we will, but that is an alkane. How did I know that? Well, I know that the alkanes are CnH2n plus 2. So if n is 10, then 2 times 10 plus 2 is 22. Kevin, my bro, how did you see that? He's so smart, dude. Guys, I've been doing this for so long, yeah, you guys probably saw it too. Okay, let's carry on. Two straight chain organic compounds X and Z are produced in. Okay, so I read that, but I wasn't actually reading that. I was still thinking how funny my joke was, but probably wasn't. Okay, so Kev, come dude. Two straight chain organic compounds X and Z. Where are they? Oh, they're there. I was looking for them in the diagram. Are produced in test tube A according to the following equation. Oh, okay, I understand. So we're taking some C10H22, which is decane, by the way. Kev, how do you know this? Okay, guys, so it's a 10 carbon. So we know from the tables that you get like ethane, propane, butane, hexane, heptane, octane, nonane, and then decane. But they just hardly ever ask us that. So you've seen that before. So, okay, so what we have the C10H22 that's chilling over here, and they're going to react it with some stuff, and it's going to produce some products, this stuff over here. Okay, so pretty much cracking. Now, we've spoken about cracking before, but what we said in cracking was, because I'll be honest, we don't often see this Al2O3, aluminium oxide, okay? So what we've seen in cracking before is that you get two types, right? We get one called thermal, and then you get one called catalytic. Now, catalytic uses a catalyst, and that's typically nickel, palladium, or platinum. If you've seen that before, that's also the catalysts that we use when we convert an alkene to an alkane by hydrogenation, okay? So we typically use one of these, not all of them, just one of them. So that's a catalyst. Then when we use thermal, we use high temperature and high pressure. Whereas with this one, we just use normal temperature, normal pressure. Okay, so seeing this is a bit random, right? So I have seen them talk about this catalyst in some textbooks, but it's not that common. So this is an alternative catalyst that we could use. But I'm surprised they are asking about that one because, as I said, you're only going to see that one in certain textbooks. It's not going to be like, you're not going to see that everywhere, okay? It's not the most popular. This is normally the catalysts that we use. But I mean, in a test, if they give you some chemicals and they give you something random like this that's not part of this reaction, then just take it as a catalyst. So we've called it a catalyst, okay? They said state the function, so they didn't say what it is. So we know it's a catalyst. But now, what do catalysts actually do, guys? Can you remember what a catalyst actually does? Well, it increases the rate of the reaction by reducing, so I'm going to say it reduces the activation energy, okay? So in grade 11, for example, we learned about it on these enthalpy diagrams where if you want the reaction to proceed, these are the reactants, whoopsie, and these are the products. But for the reaction to begin, you needed to activate the reactants and you needed to give them enough energy so that they could reach this level over here. That energy gap was called activation energy. When you use a catalyst, that becomes lower. And so it can instead of going all the way up to the top, it can actually just go up to here and then go that way. Okay? So a catalyst reduces the activation energy. Let's carry on. The organic compounds X and Z are now passed through bromine water. Okay, so just remember that when you crack, we didn't even talk about this. I didn't talk about this when I first read this, but cracking is when you take this molecule and you break it up into smaller molecules. So for example, this might be like, I'm just guessing, I'm not saying it is the answer, but it could be like C3H8, and then this could be something else, okay, for example. So it says the organic compounds X and Z are now passed through bromine water. This sounds like the bromine water test. I wonder if you've heard about that. If not, let me talk to you about that so long. What scientists do is, in real life, is they do the following. Let's say you've got two solutions, this one and this one, okay? Now, one of these is, let's say this one is an alkene, which has double bonds, and this one is an alkane. But let's say that the scientist does not know. They don't know which one is which, okay? And alkanes, obviously, they just have single bonds. Now, scientists sometimes get the scenario where they've got these two solutions in front of them, but they don't know which one is the alkene. Let me write this better. So we said alkene, alkane for this one. My bad. And this one is the alkene with double bonds. Okay. So what they do, okay, is... Now this is where you need to understand your chemical reactions quite well. If you do understand your chemical reactions quite well, if you take an alkane, okay, so let's go draw out an alkane, for example. I'm not going to draw the hydrogens in. If you react that with a halogen, such as bromine, okay, because halogen is a bromine, it can produce a haloalkane only if, what's the reaction condition? Can you remember? If we have enough UV light or if we have enough heat, okay? But if you think about your alkenes now, remember I've said that cringy joke before. Maybe you've heard it, maybe you haven't. But alkenes are very keen to react. What that means is that they love to react. Alkenes are like, bro, like, who can I react with? What can I react with? I just want to react with everything because I've got a double bond and I just want to use my double bond to react, okay? So that's alkenes. So alkenes have that double bond, like we said. And so they react with a whole bunch of stuff. They can react with water to produce alcohols. They can add on, you can add on halogens, you can add on hydrogens. There's a whole bunch of stuff that we can add on. And so, for example, you could definitely react it with Br2, and maybe one of these, you could even think about both of them, but usually one of these would land up on here, and then, you could have like a Br here, and then another Br ending up over here, and then the double bond breaks, for example. Now, that process takes place very easily. You don't need much, because alkenes are very keen to react. So this one, you need quite a lot of, you need UV light from the sun, or you need a lot of heat. This one, you don't need much. It takes place very easily. So what scientists do, these smart guys or gals, is they take these two liquids, right? They take them, and they put them into a dark room, like a dark cupboard. They put them inside a dark cupboard. And they then come back, maybe in 24 hours or so, and they see if a reaction has taken place. Because remember, bromine liquid is orange. I don't know if you remember that. It's orange. So when you throw it inside here, the whole liquid is going to become orange for this one and for this one. Then they place it in the dark cupboard and they come back the next day. This one, would a reaction have taken place or not if they put it in a dark cupboard? Well, yes, because we said that this one reacts easily. It doesn't need much. So that means that the orange is going to have disappeared because all of the orange has reacted. The Br2 is no longer the Br2 because it's reacted. However, this solution will still be orange because the dark room means that there's no sunlight and there's no heat. The heat is like when they put like a flame or something like that. So nothing would happen over here. So when the scientist reopens this or has a look at this solution in the morning or in the 24 hours, this one would still be orange because nothing has happened. So the orange bromine is still going to be there. Does that make sense? I hope that makes sense. And that is how this bromine liquid test actually works. Okay, so we said that we're producing two of these things over here, okay? Now, I don't know if you can remember, but when we explained cracking in one of our earlier videos, we know that when you crack an alkane, okay? When you crack an alkane, you normally produce an alkene and an alkane. So my guess is that one of these is going to be an alkene and one of these is going to be an alkane. They then take both of those and they pass it through bromine water at room temperature in test tube B. Okay, so here's test tube B. So we can see that they had a reaction. The products, which are these two, are then going to be passed down. So here comes the X and the Z, and they go into this solution over here. Now they're saying that it's at room temperature. So that means that there's no heat, like there's no severe heat, and there's no sunlight. Okay, we assume that it's in a room. So, and they tell us that only B Sorry, that was random. Only X, only compound X reacts. So you got to think to yourself, what is compound X then? Would that be the alkane? Or let's say, would that be an alkene? Or is that an alkane? Well, the fact that it reacts, I'm hoping you know that that means it's an alkene. So compound X is an alkene, okay? So they say apart from gas bubbles, what other change would you see in test tube B? Well, we would see the orange bromine liquid. You would see the orange liquid become colorless. Why? Because a reaction is taking place and all the bromine is reacting. And so the bromine is disappearing because it's being used up in the chemical reaction. Okay, so we've just figured out that X is the alkene, or it is a alkene. Okay, and it says, this question says, write down the type of reaction that takes place in this test tube. Well, we know that alkenes are keen to react, like we've said. And what they do is they like to have things being added onto them. So for example, if you take this alkene, okay, let's go draw it out. This is just an example. If you react that with water, I'm going to draw water like this. This is just an example. We know that this OH, or let's start with this hydrogen, according to Markovnikov's rule, that hydrogen would go there, okay? Because remember, the richer get richer. So this hydrogen would go there, according to Markovnikov's rule. Remember the whole richer get richer? So this carbon already has 2 hydrogens. So it would, because it's the richest, whereas this one only has 1. So the richer get even richer, and then the OH would go over there. This is just an example once again. So can you see what we did? We took an alkene, and then we added molecules onto it, okay? So alkenes love to react, and they love having molecules added. So they love to undergo addition. So that's what you could say here. Addition. You could also, if you wanted to, realize that in this example, we are adding bromine. So I'm just going to write it like that. I know it's Br2. So what would happen is you would originally have that, okay? And then one of the BRs would go there, and another BR would go there. So we're adding halogens. So you could also call this halogenation, like that. Okay, so once again, remember that X is a alkene. All right. So it says, for 3 marks, write down the molecular formula of compound Z. So compound Z would have to be an alkane. When I sat and read this, I was like, bro, this question could have multiple answers. Then I went and looked at the memo, and it does have multiple answers. So there's more than one answer here. For example scenario 1. Let's say that X is C2H4. Then you would have, okay, now think about this carefully. There are 10 carbons on the left. Here we've got 4 because there's 2 and then you times that by 2. So this one would have to have 6, okay? And then here you've got 8 hydrogens, right? So then 22 minus 8 is, what's that, 14. So then you would have that. So that is one answer, C6H14, okay? But what if X was, okay, so that's one scenario, but what if X was C3H6? Why am I doubling it? Well, remember, alkenes are CnH2n. If you don't know that, or if you forget that, just go draw out a 3-carbon alkene, go put all the hydrogens, and you would see that they are 6, okay? So maybe that's what X is, okay? So then you would have C10H22 gives you 2, okay? So here you've got 6 carbons. Here you've got 10. So that means this would have to have 4 carbons. And then here you've got 12 hydrogens because it's 2 times 6. So then you would have to have 10 over here. So that's another possibility, okay? And then the third possibility is, what if X is C4H8? Once again, if you want to go draw out that alkene with a double bond, 4 carbons, you would see that it can only fit in 8 hydrogens. Well, then what we would have is that over there. So then you're going to have, here you've got, on this side you've got 10 carbons. On this side you've got 8, because it's 2 times 4. So here you would have 2. And then here you've got 16 hydrogens. So you would have 6 over here. And so that's another possibility. Okay, now we wouldn't go any further, because if I change this to a C5, then you can imagine if that's C5 and H10, then all of the carbons have been taken. There would be 10 carbons there and 10 carbons there, so that wouldn't work, because then this would have nothing. I'm not going to go too much into this, but there are some of you that might say, well, if this one is C5H10, then that could work if this one is just going to become H2. I hear what you're saying, but they said that the two products, X and Z, are organic compounds. Organic compounds contain carbon. So this wouldn't be an organic compound. Okay, so the three answers would be any one of those. You don't have to give all of them, just one of them. Okay, this one says, write down the structural formula of X. Well, we have to remember what we got for our previous answer. We said it was either that, or that, or that. So depending on which of these you chose would affect which of these you chose. Okay? So I'm going to just choose one of them, if you don't mind. You can just sort of follow along and try. Actually, no, I can't do that. I will show all of them. Okay? So if Z is C6H14, then what we said was this would have to be C2 and then H4. Okay, so if it's C2H4, then you would write it like that and then like that. You can put the H going down or to the side of here, it doesn't matter. And so that is what your structural formula would look like for X if you chose this for Z. Okay, that's the first. That some students would have gotten like that. Now, if you chose C4H10, so C4H10, then what you would have gotten is you would have gotten that C3H6 over there. So if you had to go draw that out, it's just got a double bond on one of them, and then if you had to go fill in all the hydrogens, then that is what your answer would be. That's if you chose C4H10 as your Z. Okay, and then lastly, if you chose Z as C2H6, well then you would have gotten C4H8 over here. And so if you had to go draw that out, then that would give you C4. So we put a double bond, because it's an alkene, right? We said that. And then you would get like that, and then hydrogens everywhere, and there we go. So this is what your answer would be if you chose that for Z. Okay, so 3 different answers, but you only have to give one of them. This question will be split up onto different pages, but for those of you that just want to see all the questions we're going to be doing, here they are. So it says that learners use the reaction MgCO3 with excess HCl to investigate the relationship between temperature and rate of a reaction. And then here is the equation or the reaction that is taking place, and let's just see. So yeah, typically they like to do these reactions where you have a acid and then some type of base, like a metal carbonate, because when you take a metal carbonate, for example, and you react it with an acid, it always produces a salt, water, and CO2. Now the CO2 is a gas, and they love to use questions where they measure how much gas is produced, for example. And so here you can see average rate of CO2 that they measure. Okay, that's just typically what I see over and over and over. Sometimes they don't use like a metal carbonate, but they use just a normal solid like zinc, or something like that, which is a metal. And we know that if you take a metal and you react it with an acid, you produce a salt and hydrogen gas. That's another one that I see quite often. Okay, but I think I'm getting a little bit ahead of myself. Let's see what they actually want us to do today. So it says the results obtained are represented in the graph. Okay. So let's move on now to where I split the questions up. So the first question says, define the term rate of reaction. So I'll get the definition for us now, but rate just means how fast. Now, there are a whole lot of different things you can say, and on the memo, they even give a whole lot of different things that you could say. So what you should say is the following. It is the change in... So I thought instead of writing it out, let me just show you. So, okay, so the first one is, and they said you can choose any one. So the first one is you could say change in concentration of products, or you could say change in concentration of reactants per unit time, or just per time, for example. The other option is that you say it is the change in the amount, or you could say the number of moles. You could use volume, or you could use mass. You don't have to use all of those. They're giving you options. So you could say amount of moles of products or reactants per unit time, okay? So you can choose whichever one you prefer over there, but there were, those are the different options that we can choose when defining the rate of a reaction. Okay, now this question over here says, state 2 conditions that must be kept constant during this investigation. Okay, so in this investigation, we are investigating the relationship between temperature and the rate of the chemical reaction. So that is the variable that they are changing. They are running this. So remember, reaction rate can be affected by many different things, such as concentration, pressure, using a catalyst or not using a catalyst, temperature, surface area, like are we using a solid or are we using a powder? Okay, these are all different factors which make reaction rates faster or slower. However, the goal of this experiment is to investigate the relationship with temperature. So that is the only variable that we need to be changing. We're either going to make it a bit more hot or a little bit more cold. That's the only variable we're going to change. So the other variables, such as concentration of your hydrochloric acid, these need to remain constant. The pressure, for example, the use of a catalyst, we don't change that. And then the nature of this, the solid, because remember this is a solid, so you could either have it as a big piece or you could have it as a little bit of a powder. So you could say the nature of the MgCO3. We don't look at these ones because these are products. We can't change the products. Okay, the products are they are the byproduct, excuse the pun, of what we do here. So once again, we're not going to change the concentration of this because we are only affecting temperature. We're not going to change the pressure in the system. We're not going to change the use of a catalyst. So like if we're going to use a catalyst, then only use a catalyst. Use a catalyst for all of the experiments. If we're not going to use a catalyst, then don't use a catalyst for any of the experiments, okay? But don't use one experiment with a catalyst and then one experiment without a catalyst, okay? So they must choose what they're going to do. And then if they decide what they're going to do with the MgCO3, either they're going to keep it as a big piece of solid or they're going to grind it up into a powder. They can choose whatever they want, but then they must keep it the same for the whole experiment, for all of the experiments. They mustn't change that. The only thing that's changing is the temperature. Oh, and then another thing, how much of the MgCO3 and how much of the HCl we're using. We must not change that either. So we can add that as another option, amount of HCl and MgCO3. Okay, so they said give 2, but I've given you all the possibilities. Okay, here we go. 4 marks. Use the collision theory. Okay, so remember what the collision theory tells us. It tells us, I'm not answering their question now. I'm just giving you some like a bit of a background theory in case you're busy studying or preparing for something. Okay, so this is not the answer to this question. I'm just quickly showing you something. So the collision theory, think about the word collision. It's literally when you have a molecule and another molecule that collide. The collision theory tells us that in order for a chemical reaction to take place, you need 3 things to be in place. Number 1, the objects have to bump into each other. That should be pretty obvious to you. So the objects must collide. They must go into each other. But that is not enough. That is not good enough. They have to have the correct orientation. For example, maybe this one does something like that, and this one does something like that. Then when they collide, maybe this part slips into that part, for example. Like, I don't know how it works, like how the chemicals are really working, but I'm just using an example. For example, let's draw that again. So if this part if this molecule collides with that molecule, then it fits in perfectly. You remember how, like, as kids we used to play Tetris where the blocks fit perfectly? But maybe if this block was facing the wrong direction, like maybe this block is, I can't draw. Maybe that block's like that. Then when this one and this one collide, they're just going to bounce off of each other because they're not going to fit into each other properly. So the orientation is wrong. So they need to have the correct orientation. And then the last thing, remember that when you want a chemical reaction to take place, you need to be able to have your molecules at this energy part over here called the activated complex. And to get there, you need enough energy. Okay? So these molecules need to have enough energy. Let's write that out better. They need enough energy. They need enough energy. So the collision theory tells us that these are the three things that we need in order for a chemical reaction to be able to take place. Okay, so now let's read what their question says. It says, use the collision theory to explain the relationship shown in the graph. So, okay, so what we can see in this graph is that we are increasing the temperature, okay, on the x-axis. That was our independent variable. That is what they said we were going to change. And so what we can see here, for example, is that, and then here they're telling us the average rate of CO2 production in grams per minute. So you need to understand this graph. It says that if you run this experiment at, let's say you run this experiment at 20 degrees Celsius, then if you read off the this value, let's just say, I'm not saying it's exact, I'm just saying it as an example. If this is 0.14, then what it means is that if you run this experiment at 20 degrees Celsius, then your rate of production of CO2 will be 0.14 grams every minute. Okay? If you then decide to run this reaction at 40 degrees Celsius, then you will produce, so if you run it at 40 degrees Celsius, then you are going to produce the CO2 at 0.5 grams every minute. If you then decide to run this at, 10 degrees Celsius, then your rate of production is going to be less for CO2. They're not saying you're going to make less CO2, they're saying that you're going to make it slower, the grams per minute. So your grams per minute will become less, okay? So what they're saying is that what we're seeing is that the higher the temperature, the higher the rate. Remember what rate is? It's how fast you can make something. So the higher the temperature, the faster the CO2 gets produced. So let's think about that from a collision theory point of view. If you make the temperature inside a container higher, so if you have a container, okay, let's say we have a container, okay, and you've got molecules moving around. If you increase the temperature, what happens to those molecules? Well, if you increase the temperature, they are going to move faster because they're going to have more kinetic energy. Okay, so the molecules are going to move faster. Does that not mean that they're going to collide more often? Yes. Does that change their orientation? No, it doesn't. You can't say, like let's say for example, this molecule looks like this. Just because you increase the temperature doesn't mean it's going to make it look different. So we can't change the orientation. You could never do that. And then by increasing the temperature, do we not give the molecules more energy? And so it'll be easier for the molecules to have the activation energy that they need to react? Yes. So that is what temperature does. It makes the molecules move faster. So I will write this down now, guys. I'm just explaining. So if they just chill, bro. Just take a chill pill, okay? So, but Kevin, I've got my exam in like 6 minutes, bro. Come on, the teacher's calling me. Sorry, guys. Just wait, okay? I'm getting there. So I'm getting nervous now. Okay, just chill, Kev. Maybe you need a chill, bro. Okay. So, we said that if you increase the temperature, these molecules, they're gonna move faster. That's just what temperature does, right? If you add more energy into the system in the terms of, if you increase the temperature, you add more energy to the system, they move faster because temperature is a measure of average kinetic energy. So the molecules are gonna move faster. That means that they are naturally gonna move in, they're gonna bump into each other. It's gonna be chaotic in that container. They're all gonna be like, whoop, sorry, coming through. Sorry, Bob. Morning, how are you? How are your kids? Sorry, I bumped into you too. How are you, Tony? So it's going to be pretty crazy. Everyone's going to be bumping into each other because they're moving around so quickly, okay? Yeah, I'm pretty random, aren't I? And then for this one over here, the orientation, we're not going to worry about that one. And then they're going to have more energy now, okay? Because we said that for a chemical reaction to happen, the molecules need to be activated to the activation complex, so they need more energy. So obviously, if you've given them higher temperature, they've got more energy in the form of kinetic energy. Okay, so with that being said, let's go put this into words so we can get our 4 marks. So let's first explain to them what we see on the graph, okay? On the graph, it can be seen that the rate of CO2 production increases with temperature. Okay, I'm going to take this out. Now we can say that an increase in temperature, and guys, you don't have to say it exactly like I do, an increase in temperature causes the molecules to have more kinetic energy. Okay. Oh, something important that I wanted to mention. You know how I said that number 1, you need the molecules to collide. Number 2, they need the correct orientation. And number 3, they need enough energy. Okay. Now, remember I said that when you increase the temperature, they're going to collide more often, right? But then I said that that doesn't have any effect on the orientation. But what I forgot to mention there was, in chemistry, you get 2 types of collisions. You get one that's successful, that's called an effective collision, and then you get a collision that is not successful, and that's called ineffective. So you could imagine that if you've got a molecule that looks like this, colliding with a molecule that looks like that, that's going to be effective. It's going to be a good collision because this part and this part are going to link up perfectly, okay? So that would be called an effective collision. But if you had like a molecule, for example, that looks like this, and then colliding with a molecule that looks like that, well, that's not really going to be an effective collision because this part and this part are not going to link up nicely. So that's called ineffective, okay? So, would you agree with me that if we can increase the number of molecules that are colliding by making them move around faster, they are going to bump into each other more often, right? So doesn't that mean that we will have more effective collisions taking place compared with if the molecules were just moving around slowly? Like if you sit there for 1 hour and you watch them, because they're bumping into each other more often, we would expect that we will see more effective collisions taking place because there's just more collisions, right? Okay, so what we can then say is that more effective collisions will take place. Okay, so more effective collisions will take place, and then the next thing, okay, so we've spoken about the fact that they're going to be moving faster, or having more kinetic energy, and we also explained that there's going to be more effective collisions. The next thing is that with an increase in temperature, we can say that an increase in temperature also allows more molecules to overcome the activation energy, which also leads to more effective collisions. Because once again, if 2 molecules collide, but they don't have the right amount of energy, well, that's going to be called ineffective, leads to more effective collisions. Okay, so therefore, rate of CO2 production increases with, I'm just going to squeeze this in here, guys, an increase in temperature. Okay? Oh, and then something I forgot, something that they do like to see on the memo is over here. More effective collisions. And then when you say more effective collisions, just add in over here per unit time. So more effective collisions per unit time will take place, which also leads to more effective collisions. And then over here, just say per unit time. Okay, I've added a little bit extra here. This is worth more than 4 marks, to be honest, what I've given you. But I just want you to have the full understanding of the reasoning behind this question. This question says that the learners obtained the graph above using 5 grams of MgCO3 with excess HCl. Okay, so we know that we are at a temperature of 40 degrees. So we're going to use this 40 degrees over here. So we can go up and then across, and it's perfectly on that line at 0.5. Okay, so that 0.5 is the grams per minute of CO2. It's not the grams of CO2, it's the grams per minute. So we can come back to that value a little bit later, because what we're going to do now is, so what they tell us here is that 5 grams of Mg or magnesium carbonate, and then they're using excess HCl. Okay, so that means that we don't know how much HCl we're going to use, so we're just going to ignore that part. But we do know that if the HCl is the excess, then this one must be the limiting. And what do we know about a limiting reactant? We use all of it. So we are going to use all of this MgCO3. And so what we can do is we can take this 5 grams and we can use the mole formula, which is N equals to M over capital M. And we can use that 5 grams and go work out the moles of MgCO3. So to work out the molar mass, we could take the magnesium, which is 24, plus carbon, which is 12, and then 3 oxygens, which would be 16 times 3, which is 48. If you calculate that, we get 84 grams per mole. Okay, so what we can now do is we can say that the number of moles will be equal to the mass that they gave us, which is 5, over the molar mass, which is 84. And if you work that out, let's actually leave it as a fraction for now, okay? So that means the moles of MgCO3 is 5 over 84. What we can now do is look at the mole ratio of this one and this one, and we can see that they are in a 1:1 ratio. So therefore, the moles of CO2 will also be 5 over 84. But that is the moles that is produced, because it's the product. So think about this carefully. And I think just to make it look a little bit better, let's easier to work with, let's round this off now. I'm going to use these many or that many decimal places because it's not the final answer. Okay, so that's how many moles of CO2 we produced. Now they tell us that this reaction can produce 0.5 grams of CO2 per minute. Okay, it's grams per minute. So let's go work this out in grams so long. So we're going to use this formula again. Okay, and to work out the M of CO2, or the molar mass of CO2, it's going to be carbon, which is 12. I'm not going to put the periodic table up now, but carbon is 12, and then there's 2 oxygens, which are both 16. So that would be 32, and that would give you 44 for carbon, for CO2. So what we can then do is we can say 0.0595 equals to the mass, which we don't know, over the molar mass, which is 44. And so if you had to get the mass alone, you would say 0.0595 multiplied by 44, and that would be 2.618 grams. So think about this carefully. We know that we have produced 2.618 grams of CO2. They tell us over here, if we work at 40 degrees, that the CO2 production will be 0.5 grams per minute. So that is the rate of this reaction. The rate is 0.5 grams per minute. Whoa, what was that? Per minute. So that means in 1 minute, there would be 0.5 grams. In 2 minutes, they would have 1 gram. In 3 minutes, they would have 1.5 grams. In 4 minutes, they would have 2 grams. So you get the idea, right? They're producing 0.5 grams per minute. So then to work out the number of minutes that it's going to take us, you could take this number and you could divide it by that number. So the time, okay, let's make some space here. So the time would then be 2.618 divided by 0.5, and it's going to be a little bit more than 5 minutes if you just think about what we were doing here. Okay, so if we round off, it'll be 5.24 minutes. Now, because of rounding off and all of those types of things at different, different schools, different teachers round off at different places. So the 5.24 is not the only answer that you can get. You are allowed to get an answer anywhere between 5.238 all the way up to 5.28 minutes. This question says, calculate the molar gas volume. Now, what is molar gas volume? Well, you know that formula that goes N equals to V over Vm? That is molar gas volume. Now, some of you are like, my bro, my home dog, isn't that value going to be 22.4? That's what my teacher said. Guys, this is only going to be 22.4 decimeters at STP. We are not at STP is like 0 degrees Celsius and a certain pressure, which isn't important right now. But STP, they'll say STP. Then this is going to be 22.4. That's your molar gas volume. But we're not at 0 degrees Celsius. We are at 40 degrees Celsius. So this number is completely irrelevant to us. Okay? So we're going to use the formula anyways, but we're not going to use 22.4. They're talking about CO2, so we know how many moles of CO2 we produced. In the previous question, we had it over here. Okay, 0.0595. You might have a different rounded value, 0.0595. The volume that we collected was 1.5. And then we can calculate the new Vm at 40 degrees. And so to do this, you would take this to the left-hand side. So you're going to end up with 0.0595 Vm equals to 1.5. And then to get Vm alone, you're going to say 1.5 divided by 0.0595. And that would give you 25.21 decimeters. So it makes sense that it's a little bit more than 22.4 because that is the molar gas volume at 0 degrees. But as you make your temperature larger, the gas molecules can expand a little bit further apart because they have more energy due to the temperature. So 1 mole of a gas at 40 degrees would occupy a larger volume than 1 mole of a gas at 0 degrees Celsius. Because this is a molar volume, you are also allowed to say decimeter cube per mole, but on the memo they accept both. Okay, and then for those of you that maybe use different values, you can get a value between 25 up to 25,21. The graph below represents the Maxwell-Boltzmann curve for CO2 at 40 degrees Celsius. Okay, so we've seen a Maxwell-Boltzmann curve before. We've got kinetic energy, and then we've got number of CO2 particles. Now it says, redraw the graph above. Okay, wait, on the same system, I've actually sketched the curve that would be obtained at 20 degrees. So what we need to understand is that at 40 degrees and at 20 degrees, the amount of CO2 will not change. Okay, you still have the same amount of CO2 being produced in a chemical reaction, for example, the one that we saw over here. That doesn't change because we're not changing the 5 grams of MgCO3. All that's going to happen is that by changing the temperature from 40 degrees to 20 degrees, what does that do to the kinetic energy of the molecules? Well, it makes them a little bit slower, okay? So, for example, these molecules over here, which currently have a kinetic energy of, I don't know what the value is, but maybe it's like 50, for example. Well, those molecules are now going to have a lower kinetic energy. And so we're going to sort of see this part of the graph move a little bit to the left. This part's going to go a little bit left. This part's going to go a little bit left. This part's going to go a little bit left. And they're all going to go a little bit left. So as we showed with all of these parts that are going to move, you might expect the graph to just move to the left like that, for example. But for some reason, as you move to the left, the peak of the graph goes up, okay? So it's actually going to go a little bit higher and then like that, okay? And then as you move further to the right, that curve flattens out, so it becomes more like that, okay? And for reasons that go way beyond even grade 12 level, they don't expect you to know that. Just know that when the curve, I mean, they want you to know that the peak goes higher and lower, but you don't have to explain why. So if this is a normal curve, then if you make the temperature larger, the peak does something more like that. You see how it goes a little bit lower, but a little bit further to the right. And then if you make it colder, it goes higher up, but then like that. Okay? Okay, so let me just show you that again. So if I take, for example, this part, and this part, and this part, and this part, and I just shift them a little bit left, because their kinetic energy is going to become less, so I can put it there, there. Well, let's do this in x's. There, 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 and there. Okay, so then you could try draw your new curve, but for some interesting reason, which goes beyond the scope of high school chemistry, the more left that peak goes, the higher up it goes. So this peak is going to be shifted left, like we said, but then it's going to go up a little bit. So you're just going to increase its height a little bit like that. Okay, and then let's go draw. So you're going to get a graph that does something more like that. And if they increased the temperature, let's say they asked you to draw a graph of 60 degrees, for example, because this is 40 degrees, this is 20 degrees. If you go to 60 degrees, then everything becomes has more kinetic energy. So then you would get something like there, this would also move there, and then this would move there. But then this peak would actually go a little bit lower down, okay? So it would be like there. So you'd get a graph that does something like that. Okay. That's just if they gave us something like that. Initially, 4 moles of hydrogen and 4 moles of iodine are allowed to react in a sealed container, 2 decimeter container, according to the following balanced reaction. The graph below shows the concentration versus time. Okay, so on this graph, they're not showing us the iodine. They're just showing us the hydrogen and the this part over here. So the first question says, write down the value of Y. So that's over here. Now that is a concentration value. Now we know that concentration is equal to N over V. So we know that the starting moles of hydrogen is 4. And we know that the volume of the container is 2. And so that would give us 2 moles per decimeter. Okay, so let's just write that down. And we can put on the graph as well. Okay, the next one, state Le Chatelier's principle. Okay, so let's talk about Le Chatelier first, and then we will get the definition. So Le Chatelier was the person who discovered that if you have a system that is at equilibrium, okay, so think about a chemical system that is at equilibrium. That system is happy. If a human being comes along and tries to change anything in the system, such as pressure, temperature, or concentration, then the system will do whatever it can to try and stop, or not stop, but it'll try to balance out the change. So if someone comes along and increases the temperature, then the system will do whatever it can to try and decrease the temperature. If someone increases the concentration of one of the reactants, then the system will try to decrease the concentration of one of the reactants. So when a system in equilibrium is disturbed, what does disturbed mean? Disturbed means that someone changes something. Either they change the pressure, the temperature, or the concentration. So when a system that is in equilibrium is disturbed, the system will react in such a way so as to oppose the change. What does oppose mean? It means go against. So if someone increases the pressure, the system will try to decrease the pressure. If someone increases the temperature, the system will try to decrease the temperature. If someone decreases the concentration of one of the substances, then the system will try to increase the concentration of that substance and reaches a new equilibrium. Now, obviously, this one is not going to be word for word what your teacher's is, or no one has the perfect definition, okay? In the test, they are just looking for certain phrases, but you don't need to get it word for word. I know that at your school, your teacher might say that you have to get it word for word. I think that's a bit silly, but in the final exams, you don't have to have it word for word. You just have to get the correct phrases, okay? All right, this question says that changes were made to the temperature at T2. Okay, so guys, at T2 over here, a human being comes along and they do something to the system. Either, and I want you to listen very carefully in this question, because I've had learners comment on some of my videos in the past about equilibrium and especially the temperature part, and they thought that I was saying the opposite of what their teacher was saying, but it's it's a misunderstanding because those videos are correct, but there could be a misunderstanding where learners are confusing what is the system, what is changing this, what is the human being doing to the system, and then how is the system responding to that. And if you get those two parts confused, then it's going to sound like we're saying the opposite things. Okay, so listen carefully. At this point over here, okay, let's point over there. A human either increased or decreased the temperature. We don't know what they did, but that's what we're going to try to figure out. You cannot figure it out by just saying, oh, that's exothermic, hot, or something like that, okay? So that is where the person made the change. Now, we don't know what they did. Either they heated or they cooled the flask. We are going to try to figure that part out. The way that you figure that out is you see what does the system do after that. So how does the system respond after that point over there? Because if you can see how the system is responding, then you can work out what the person did over here, because Le Chatelier has told us that the system will always try to oppose the change. Okay, so what we can see if you look at the amount of HI, which is a product, after this point, the amount of HI goes up. Okay, so the amount of HI is going up. So does that mean that the forward reaction is being favored? Or does that mean the reverse is being favored at this point over here? Well, that would mean that the forward is being favored because you're making more product. Okay, so let's write that down. Forward reaction, or let's make it very clear. After the change at T2, the forward reaction gets favored. Okay, now you got to think about why the system is doing this. Remember, the system is always trying to go to the opposite of what the person did. Okay, so let's see. The forward reaction is favored. Now we know that the forward reaction is an exothermic. Okay, so let's write that down. The forward reaction is exothermic. Now you need to remember that exothermic produces heat. Okay, so you got to ask yourself, why was the system trying to produce heat? Why was it trying to produce heat in this area? Well, that would only be if this human being over here cooled the flask down. So the human being cools the flask down over here at T2. Then the system does not like that, so it tries to produce heat by favoring the exothermic reaction, because exothermic reactions produce heat. I hope that makes sense. So the answer for this first question is actually going to be cooled. Some learners will say heated because they can see that there's an exothermic. But that's not what the change was originally. They want to know what changes were made to the flask at T2. They're not asking what happened to the changes over here. They want to know what happened there. And then because of that, we can see what the system did in the response to the change. Okay? So this next question says, fully explain the answer. Okay, so we can say after the change at T2, the forward reaction gets favored. The forward reaction is exothermic, which produces heat. So then we can say, therefore, the system, or the flask, we can say the flask was originally cooled. Because as I said, a lot of learners, they're like, oh, look, exothermic, it's making it hot, so the system was heated. No, the system is only being heated after the original change, which took place over there. Okay? Alright, so with this question, I will be splitting all of the questions up onto individual pages, but for those of you that maybe just want to have a look at all of the questions in one go, there they are. So let's begin. It says the equation below represents the reversible reaction that takes place when NO2 is converted to N2O4. Initially, X moles of NO2, okay, is sealed in a 1 decimeter container. When equilibrium, okay, so it looks like this is definitely a KC kind of question. So that's definitely what we're going to be doing, but let's just have a look here. It says write down the meaning of the term reversible. So one of the definitions is that it is a reaction which can take place in both directions. Okay, so for this next one, we're definitely going to go do a KC table. Okay, so let's go make our table. So remember, our table always has reaction, initial, mole, So it's initial moles, then it's the difference, or you might call it the change. Okay, then it's your equilibrium moles, so mole at equilibrium. Okay, let me make this bigger. Okay, so there we go, that looks a lot better. And then we have our reaction is 2NO2 in the gas phase goes to N2O4 in the gas phase. Okay, and then this is a line over here. Okay, so initially we start off with X moles of NO2, and if they don't mention anything, then your product would always have a 0 for the initial. Now, they say that when equilibrium is established, 0.81 moles is present. So that means at equilibrium, your N2O4 is 0.81. So how do you go from here to here? Well, the only way you do that is by adding 0.81. But now this row is the most important row, because here you got to use your mole ratios. This is a 1 to 2, so this one would be 1, this one would be double that, okay, because it's for every 2 of these there's only going to be 1 of those. So this one's going to be 1.62, but it's going to be a negative. Why? Because it is a reactant, so it becomes less. And so here you could just say X minus 1.62. I just put those two together. And so now we can get concentration by using the C equals to N over V formula. Oh, that's not what they're asking us. What are they asking us for? Oh no, we are correct. So to get your, to use your C equals to N over V formula, you're going to say X minus 1.62, which is your moles, over your volume, which is just 1. There they tell us. And so we can just take that out actually, because if you divide by 1, it's just the same. And then here it's 0.81. Now we can go work out Kc. Kc is your concentration of your products over the concentration of your reactants, and that is at equilibrium. At equilibrium. So it's your concentrations at equilibrium. So it's these values. Okay, so that's going to give us, it's your product first, so it's the concentration of N2O4 over the concentration of NO2 to the power of 2. Because remember that with your Kc expression, these numbers in the front, those become the exponents, okay? And so we're going to say 0.81 over x minus 1.62 to the power of 2. And that is exactly what they asked us to show over there. Okay, so this question now carries on, and it says 0.79 moles. Okay, well, let's just first talk about this. We know that from the previous question, we started off with this reaction, and we had this many initial moles. Then the system reacted. Okay, this is the part where the system is busy doing all of its funky stuff, and it's busy reacting, and it's doing what it's doing. Sorry, I don't know where that comes from. And it reaches a new equilibrium. Okay, so this is equilibrium. This position over here, that is equilibrium. This is just the concentration at equilibrium. But we have to understand that this point over here is equilibrium. Okay, this point over here, this whole area, this is not equilibrium. This was just the starting point, okay? And then to reach equilibrium, the system has to have a whole bunch of changes that take place, and then it reaches equilibrium. Okay, so the big yellow block, that is equilibrium. Now, what they're going to do is they're going to take that system that is chilling in equilibrium, and they are going to do some more stuff to it. So they're going to disturb it. So this is very different to a normal Kc question. Normally we would stop at this position. But I think what they're going to do now, and I've never seen this before, well, I've seen it once, is that they are going to change the equilibrium again. So we're going to go even further, okay? So let's see what they say. They then say that they are now going to take 0.79 moles of N2O4, and they are going to add it to this equilibrium mixture. So they're going to add it to this value over here, okay? And then the system is obviously not going to be at equilibrium anymore, because what does Le Chatelier say? It says that if you have a system that is at equilibrium, which was in this yellow block, and then suddenly you change that by adding something or decreasing the temperature or changing the pressure, whatever, then the system won't be at equilibrium anymore, and it's going to try to reach the brand new equilibrium. So this could be called equilibrium number 1. they're going to reach a brand new equilibrium, which is equilibrium number 2. So we're going to make a brand new KC table. Okay, so we're going to put the initial over here. So we're going to start all over again. Initial moles. This is really interesting. I don't see these questions often. This is actually the second time I've seen a question like this in like 8 years. And then mole at the new equilibrium. So let's call this equilibrium. I'm just going to say equilib because I'm cool. Equilibrium number 2. And then I'm also going to say concentration at equilibrium number 2. Okay, now what you must understand is that this here becomes the starting position of this new equilibrium. Now this part over here is going to be 0.81, but then they also said that they're going to add 0.79. So that becomes our starting position. Now, if you were to add these two together, you end up with 1.6. Okay, and now we're just going to carry on. So I don't know how this is going to play out, but let's see what happens. They say, when the new equilibrium is established, it is found that the amount of NO2, now this is such an interesting part. Look at this, guys. They say that it is found that the amount of NO2 has increased. This one here normally goes down. That's why we used a minus over there. And this one over here usually goes up. Why? Because normally the forward reaction is favored. That's just how these questions normally take place, because we normally start with zero product. So we usually go like this. But now they tell us that this one has increased. Don't worry about that. All that it means is that the reverse is being favored. So they said that this one is going to increase by 1.2. That means that this one will decrease, because if this reverse reaction is being favored, then this one would increase and this one would decrease. Okay, it has to be like that. You can't have both of them increasing or both of them decreasing. But now remember that this column, this row, change difference and change difference is the most important one, because it uses the mole ratios of the given equation to get the values. So we said that this one's a positive and this one's going to be a negative. Now, if this one's positive 1.2 and the mole ratio is 2 to 1, then this one would be half of 1.2. It would be 0.6. So now we can just see what the new mole at equilibrium is. Remember how we normally do it? You would normally just plus these two things together, and that's how we got that. And then you would plus these two together, and then you would get that. Okay, so this one will be x minus 1.62 plus 1.2. This one will be 1.6 plus minus 0.6. So this one is just going to end up giving us a value of 1. Okay, so that'll just be a 1. And then this one will end up being x minus 0.42. Okay, and then I'm not sure if we're going to need this new equilibrium concentration, but we do know that the volume of the container from the previous question is still a 1 decimeter container. So the C equals to N over V, because the volume is a 1, your concentration will also be x minus 0.42, and this will still be 1. Okay, now, I've actually never seen a question this good. I am impressed. Because what do we do now? We know from the previous question that we worked out the Kc expression as this over here. Okay, so let's just say that this is our new equilibrium, and we can call this equilibrium number 2. Okay, so check this out, guys. Wow, this is I actually think it's too difficult. It's really challenging. So we worked out the Kc from part 1, and what they found that was as 0.81 over x minus 1.62 squared. Now we can go work out the Kc for the new expression. So we can go work out Kc number 2. Now remember, your Kc is always your product over your reactants. So it's the concentration of N2O4 over your reactants, which is NO2 to the power of 2. Now, some of you might have picked up that because this reverse reaction was being favored, what you must still do when you're doing your Kc calculation, this is still the product, okay, and this is still the reactant. You're not going to change this to the products and this to the reactants, okay? And so if we go fill this in now, it's going to be the concentration of N2O4, which is just a 1, okay, and then the concentration of this one is x minus 0.42 squared. Now here is the cracker that I think is just a little bit over the top. Can you remember what is the only thing that we can change a system or change to a system so that the value of Kc would change? I have told you this before, and I've mentioned it a few times. Temperature, or let's say only temperature changes Kc. Okay? So, if you look at the first part of the question, it was done at 350 Kelvin. This one is also done at 350 Kelvin. What this means, ladies and gentlemen, is that these two Kc values are equal. Ho-ho. So we can now go make these two equations equal to each other. Some of you right now are like, oh my goodness. I know, me too. So it's going to be like 1 minus x minus 0.42 squared. Woohoo! Craziness, absolute craziness. Okay, so let me just write that down a little bit better. Okay, so what we can do here is cross multiplication. That's always a nice thing to do. So we're just going to multiply this up there, and we're going to multiply that up there. People always ask me, Kevin, when should we do cross multiplication? It's when you have an equal sign. So you can do cross multiplication across the equal sign. If you have a fraction next to another fraction, then you don't do cross multiplication because there's no equal sign. Okay, then you would just multiply the tops and the tops and the bottoms and the bottoms. But when there is an equal sign, then you can multiply across the equal sign. Okay, so there we go. Now, what I'm going to do, there's multiple ways that you could do this, but I'm just going to multiply this bracket out, or let me just think of a nice way we can maybe do this. I'm going to square root both sides, but you don't have to do it that way. But I'm going to square root both sides. Okay, the 1 doesn't do anything, right? So I'm just going to ignore that. Okay, now you got to be careful. We don't know the square root of 0.81. So let's just leave that like that. But the square root of this part, well, that's just going to disappear because a square and a square root cancel each other. So that's just going to take the square root away from that part. On this side, on the right hand side, this 2 and this square root are going to cancel each other. So we just end up with that. Okay, now I'm just going to go type this on my calculator quickly. Oh, it's 0.9. Oh, of course. 0.9. And then x minus 0.42 equals to x minus 1.62. Okay, now it's easy. You're just going to solve. So I'm going to multiply this 0.9 in and then into this part. So that's going to be 0.378. Okay. And then I'm going to just solve for x. I'm going to take all the x's to the right, and I'm going to bring all the numbers to the left. So we would end up with negative 0.3, let's write over here, negative 0.378 plus 1.62 equals to x minus 0.9x. Okay, that's a 1 in front there. If you type this on the calculator, so we end up with 1.242. Now, if you take 1x and you minus 0.9x, that leaves you with 0.1x. If you then go get x by itself by dividing by 0.1, you end up with 12.42. Now, I don't even know what that is. What is x? X was originally moles of NO2. Okay, so we can just say 12.42 moles. Now, I will say with confidence, I've been tutoring and teaching for a long time. That's the most difficult equilibrium Kc table question I've ever seen. Wow, that was a good one. It's almost too difficult. Like, I think they overdid that one a bit. Like, sometimes I like it when they put a challenging question, and they normally do challenge it in the exams, but this was just on another level. So, I don't even think, I'm not one of those people that's just going to say, oh no, it has to be as difficult as possible, bro. Like, I don't think this one, I think this one is a little bit too over the top. But if you managed with it, excellent. I doubt they would do something like this again. I haven't seen it in all my years of teaching. I haven't seen a question like this. I doubt you would see one like this. So if you really struggled with this one, I would advise maybe going over it a few times just to make sure you understand the concept, just in case they do something similar. But sure, it's good. Two acids, HX and HY, of equal concentrations are compared. The pH of HX is 2.7 and the pH of HY is 0.7. Okay, we'll get to that now. The first question says, define an acid in terms of the Bronsted-Lowry theory. Okay, so it's not that important if you don't understand your theory for the Arrhenius and the Bronsted, but I'll make a little table for you and we can go Arrhenius and then Bronsted, and then I'll quickly give you their definitions for acids and bases. Oh, Kevin, you're such a darling. I know, guys, I know. So let's quickly go and do this. Oh, let's make it a bit better. Okay, so Arrhenius, this was the first person to start giving definitions for acids and bases. Arrhenius says that acids produce H3O plus in water. Bases, I'm just going to say here, produce OH minus in water. So Arrhenius was all about the water, okay? Bronsted comes along and his definitions are a little bit better because it's not everything in life is in water. So Bronsted's definitions are a little bit better. Bronsted says that an acid is a proton donator or a donor, and then bases are proton acceptors. Okay, so that's the basic definitions. So it says define an acid in terms of Bronsted. Okay, so we can just say acid is a proton donor. So I'm not going to go write it down, but you get the vibe. The vibe, Kev. You're so cool, brother. So acid is a proton donor. Kev, when are we hitting the jaw, bro? Okay, and I'm taking it too far. Sorry, guys, it's a Friday. Sometimes on a Friday, I don't know, you get that weekend feeling. Not that I'm a guy who clubs a lot. I mean, I actually don't club a lot at all. Maybe like, I don't know, once every 2 months, maybe? You know, it's really not that much. But yeah, sometimes I just like to say funny words, like the vibe. Okay, let's move on. I'm feeling awkward. So, this question says, which acid, HX or HY, is stronger? Okay, so we know that pH, the good old pH scale, is a good way to tell us if something is strong or weak. We know that the pH scale goes from 0 up to 14. We know that 0 is more on the acidic side, 14 is more on the basic side. So if something is very close to 0, it's like got a strong acidity. Of course, this wouldn't be a good argument if the concentrations of these two solutions were not the same, but their concentrations are the same, however their pHs are different, so they definitely have different strengths of acidity. So can I explain that to you quickly? For some of you that like really, you really want to get into like how this stuff works. For those of you that just want to know the basics, then you can ignore this part. But we know that when you put an acid in water, so let's take any random acid, okay? When you put it in water, it ionizes, okay? So it becomes H3O plus because this acid donates its hydrogen or its proton to the water molecule, and the water molecule becomes H3O. And the leftover is A minus, which is an acid that has lost its proton. Okay, now we know that the reaction can go forwards and reverse. Okay, so we know that pH is equal to negative log of H3O, the concentration of hydronium. So if an acid is strong, it means that it loves to give away protons. So if this is a strong acid, then the forward reaction is going to be very much favored. That means that you would get a lot of H3O. Okay, there would be a lot of H3O if it's a strong acid. If you put a large number over here, because remember, if the concentration of H3O is high, you're going to put that number over here. And with the negative and the way log works is the larger this number, the lower the pH is going to go. And that means it's a stronger acid because strong acids have very low pHs. Okay, 0 is a extremely strong pH or extremely strong acid. Now, if you have a weak acid, let's say you've got some type of weak acid, then what happens is that a weak acid doesn't like to give away protons. So the forward reaction will go, but then the reverse reaction is also going to go. You know why? Because this acid doesn't know what it wants to do. It gives away its proton, That's the forward reaction. And then it's like, no, I want my proton back. And then the reverse reaction gets favored. And then it goes forward because it's like, okay, fine, you can have my proton. And then it's like, no, but I want my proton back. So it's like, wake up, bro. Like, what do you want to do? Do you want to sit on your phone all day, or do you want to bench press, bruh? So, I actually went to the gym today, guys. So that's probably why I've got like gym lingo in my head, bruh. I'll bench press you for a warm-up. Okay, come, Kev, we need to get serious. These people need to know their work. Okay, so if it was, as we said, if it's a weak acid, it's not really going to be committed in going in the forward direction, okay? It might go a little bit in this direction. So the point is that this concentration would end up being low, much lower, and when you plug a small number into here, because of the negative and because of the way log works, you actually end up getting a larger value. And so the value is going to be more like over here, closer to 7, and so that's a weak acid. I just dropped some bombs on you guys now, like some really important information. So if you are zoned out right now, or picturing if you could bench more than me, then maybe you need to rewind and just double check that, okay? So come at me, bro. Okay, so I seriously need to focus. So the summary of all of that, if you did understand what I said, is that the lower the pH, the stronger the acid. Okay, so if you just look at these two values, 2.7, 0.7, HY is definitely going to be the stronger acid. So it says HY, and then it says give a reason for your answer. Just say because. Okay, no, you can't do that. It's going to be HY, and just say it has a lower pH. It has a lower pH. So this question says that acid HX ionizes in water according to the following equation. Okay, now we know that that's how acids ionize. Remember I showed you earlier, if you have like HA plus water, then this acid likes to give away its proton, so it becomes that, and then you would end up with this one getting that proton, so it would become H3O plus. Okay, so it says the Ka value is simply a value that tells you how strong or weak an acid is, for example. Okay, so remember, your Ka value is actually just a Kc value for acids. So if you had to go work out Kc for this expression over here, then so remember, with Kc, which is from equilibrium, it is your products, your concentration of your products over your concentration of your reactants. And remember that we only look at gases, and we only look at aqueous. Let me just write that a little bit better. I don't know what's going on. Gases and aqueous, okay? If you have anything with liquid or solid, we don't include that in your Kc calculation, aka don't include that. So we can say that Kc then is going to be your products, which is your H3O and X minus. So we can say square bracket and then X minus over your reactants. But now remember, don't include liquids, so it's just going to be HX. There we go. So that is what Kc is, but then because it's an acid, we just change it to Ka. That's all it is, okay? Now, they tell us that value is 1.8 times 10 to the negative 5. 1.8 times 10 to the negative 5. Okay, now if you just go back to like grade 6 kind of maths, where you just think about how to make fractions big, we know that if you have a big number at the top, so if in your numerator and denominator, if you have a big number at the top and a small number at the bottom, and you divide them, you end up with a big number. So for example, if you have like 50 divided by 2, that would give you 25. But if you have 50 divided by a bigger number at the bottom, like 10, instead of a 2, you make it a little bit bigger, then it's only going to give you 5. You see? So if you make this number larger, then your answer becomes smaller. Okay? Now, if you have the same number at the top and at the bottom, then your answer will become a 1. If the number at the bottom is bigger, then your answer becomes smaller than 1. If your number at the top is bigger, then your answer becomes bigger than 1. Okay? If your numbers are the same, then it's equal to 1. So remember that. So if your numerator is bigger than your denominator, then the answer will be bigger than 1. Let's write it in normal English. If your numerator is bigger than denominator, then your answer bigger than 1. Okay? If your numerator is equal to your denominator, then your answer will be equal to 1. And then if your numerator smaller than denominator, then the answer will be less than 1. Okay, that's just how fractions work. So they tell us that the Ka value is 1.8 times 10 to the negative 5. Now, if you go type that on the calculator, well, if you just think about that number, that's the same as 0,00018. So that number is smaller than 1. So because it's smaller than 1, we're getting a situation like this where your numerator is going to be smaller. So your numerator, which is the top part, is going to be smaller than your denominator. So they say, is the concentration of the hydronium higher than, lower than, or equal to the concentration of this one? Well, we just said that the denominator is going to be larger. And so if your denominator is larger, then the concentration of hydronium ion is going to be smaller than the concentration of your HX. And so we can just say smaller, and then we can just say because the value of Ka is smaller than 1. So here we have a typical acid-base exam question where we're going to have a 7 marker coming our way. Love it. Okay, so they tell us that learners add 150 centimeter cube of sodium hydroxide of unknown concentration. Okay, so here it is. There's the 150 centimeter cube of NaOH, which is sodium hydroxide with an unknown concentration, and they add it to this hydrochloric acid solution. Okay, so there we can see the hydrochloric acid solution. Okay, and they're obviously going to mix it up, blah, 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 blah. And they find that the pH of the final solution is 2. Assume that the volumes are additive. Don't worry about that. That's only something you'd have to think about in like higher levels of university. So let me just not even go there. And then it says that the balanced equation for this reaction is that. I mean, we may talk about this one just now. It might come in where I'll say, see guys, that's what they meant. And then, okay, here's the equation. And okay, so that's quite interesting. It looks like an interesting question. So the first question says, calculate the concentration of the hydronium ions in the final solution. Okay, so we know the formula pH is equal to negative log of hydronium ions. So if we know the pH, then we can work out the concentration of H3O+, because remember, this in the square bracket means concentration. So we can say 2 equals to negative log of H3O. Now, how do we do this? Okay, well, what you must remember is that when you have a log where they have not given you a base, then it's always going to be a 10. So first step, take the negative to the other side. So put it over there, okay? If that's not comfortable for you, you can almost imagine that I take this part to the left and I take this part to the right. Then you would still end up with a positive log and a negative 2. Now you just got to remember the following. So with the way logs work, to get this part over here, let me actually write it on the other side here. You're going to say the base, which is 10, to the other side, which is negative 2. And so H3O concentration is going to be, now you can just type this on your calculator, but it would be 0. Let me get myself some more space, 0,01, and then the mole per decimeter. And now here comes this next one. So it's a nice 7-mark question. Ooh, I am excited. You know why I'm excited? Because I've told you this before. When I'm doing these questions with you right now, it's the first time I'm actually doing this question. I don't do it first and then make the video. I'm doing it now with you. So, you know, I haven't done it yet. So I'm excited to see how this one goes. Okay, so we know the concentration of hydronium in this solution. Why does that feel weird? Why am I writing it like that? Oh, because I'm saying concentration. Okay, there we go. Everything was feeling weird there. 0.01 mole per decimeter. Okay, so, right. So this question for 7 marks says, what is the initial concentration of this one? Okay, so now I'll be honest. I have absolutely no idea how this question is going to go. I don't know where to start. But there's usually only certain things that we could do. This question is going to follow very similar concepts to what I explained in one of my videos where I spoke about pH with limiting reactants. I'm going to explain it all now anyways, but that is a video that I have made, and that explains all the concepts that we're going to look at now. So here, let's have a talk about this. So we get 3 different scenarios, okay? Scenario 1, Scenario 2, and Scenario 3. So in Scenario 1, let's say you have perfect amounts of acid, base. I'm not necessarily saying the volumes have to be the same. I'm just saying that the correct stoichiometric amount needs to be present. So what would happen is, let's say you take an acid and you take a base and you add just the right amount of each one, so that we know that acids and bases react with each other and they neutralize each other. So if we have the perfect amount of acid and base, then what would you get at the final solution? Well, in the final solution, there would be no acid and no base. There will be no leftovers. So then what would your pH typically be? Well, your pH would typically be 7. That is like a perfect neutral solution, which is not too acidic, it's not too basic, it's perfectly in the middle. Okay, but now in scenario 2, so okay, let's just first label scenario 1 as equal, or let's just say just the right amount. I don't want you to think that I'm saying that it's the equal volumes, because, you know, from the ratio of acids and bases reacting each other, sometimes the ratio is 2 to 1, for example, okay? But what I'm saying is if we add just the right amount so that there's no leftovers, okay? So just the right amount. Okay, now, see, now this is why you should have listened when they were reading you Goldilocks and, what do they call it? What's that story called? Goldilocks. Is it just called Goldilocks? Was it Goldilocks and the Porridge, or Goldilocks and the Bears? Are there bears? Why am I thinking of bears now? I don't know. But I know that with Goldilocks, there was the porridge could either be just right, or it could have been too cold or too hot. Something like that. I don't know. I think my childhood, something's wrong there. Can't remember anything. But let's see. So let's go to scenario 2, where maybe you guys don't even know about Goldilocks anymore. I don't know. When I was young, back in the day, in the I can actually say in the 1900s, because I was born in the 1900s, there was a story called Goldilocks, and it was about this person who wanted the porridge to be just the right temperature, I think. Not too hot, not too cold, but just right. Yeah, so maybe... Okay, I don't know where I'm going with the story. Let's just carry on. Okay, so now let's say in this one we add too much acid. Too much acid. Do you guys also struggle with when to use 2 O's and when to use 1? I'm not 100% confident about this. Too much acid, okay? So if you add to it, let's see what that would look like. So let's say you've got a little bit of base and you've got lots of acid. So then what would happen? Well, the acid and the base would still react with each other, right? They would see each other and they would be like, yo, bro, what's up? Let's fight. And they would fight each other and they would destroy each other. But at the end of the battle, there would still be a little bit of acid left over. There would be acid left over because there was more than enough acid. So what this would do is it would cause your pH to become less than 7. Let me say less than 7, because some students still struggle with this, and all of that stuff. So the pH would become less than 7 because acids are lower pH. Okay, now when you've got too much base, if you've got too much base, then obviously what that would look like is you would have a small amount of acid, large amount of base, and so they would fight each other, they would fight, and then they would neutralize each other, but at the end, there would still be a little bit of base left over in the container. Not all of it, obviously it will be less than what it originally was, but because there's only base left over, the pH would be larger than 7. Larger than 7. Now, I'm not done with this part. What we need to understand is that in this scenario, you've got acid floating around. Okay, so you've got a whole bunch of acid floating around. Now, acids are typically like HA. Now, what do acids do in water? I'm hoping your brain literally just said, Kevin, they ionize, because that means I've brainwashed you enough, and that's a good thing, well, at least for your academics purposes anyways. So we can say then that acids ionize. So what would happen is that this acid, which is the leftover from this reaction. So it's not all of the acid that was over here, it's the leftover acid. That leftover acid is going to be like, oh man, I've just had a fight with the base, I destroyed the base. Now what am I supposed to do? Let me go ionize with the water. So this is the leftover acid from this reaction, okay? So maybe this one had 10 moles of acid, and then this is like the 3 moles of acid that's left over, okay? So it's not the original acid amount, it's the leftover amount. So that leftover amount is going to go react with surrounding water, and we're going to produce H3O and A negative, for example. And this is the part that causes the pH to go down. Okay, now in this scenario, there's leftover base. So it's not all of the base, it's the leftover base after these two had a reaction. So that leftover base, now bases typically have, for example, like NaOH. That base is going to start doing what? Well, it's going to start to dissociate, because remember, this base is chilling there and it's like, I've just had this fight with the acid, I destroyed all of the acid, what am I supposed to do now? Oh yes, I'm a base, let's go dissociate. So dissociation just looks like this. So it produces these OH minuses, and those OH minuses is what contributes to the pH going up. So, and remember, this is the leftover base and this is the leftover acid. Okay, so hope that makes sense. Acid and base, they fight. If there's leftover acid, it will ionize in the water. If there's leftover base, it'll dissociate in the water. Make sense? Perfect. Let's go back to our question now. So, once upon a time, this base and this acid were thrown into a container together, like we see over here. What did they do? They fight. They keep fighting until one of the 3 scenarios is achieved. Either equal amounts of them have been destroyed, one of them stays alive, such as the acid, or maybe the base stays alive afterwards. I can tell you who was the winner in that reaction, because if I look at these two, I know that the pH is 2 in the final solution. If you think about that, the pH is 2, what does that mean? It means that because the pH is less than 7 in the final solution, it means that the acid was the winner, okay? And we know then that this reaction over here would have taken place in that solution after these two have had a fight with each other. So what we can now do is realize, like we said, that when these two NaOH and HCl reacted with each other inside this container, there was some HCl that was left over, and we know that that HCl would have undergone ionization with water to become H3O plus Cl minus. Okay, now we can also show this like that instead. Okay, so what we can do is, if we know the concentration of H3O plus, okay, in this container, and we also know the volume of this container. How much is the volume of this container? Well, they threw all of this liquid and they threw all of this liquid together into one container. So you can just add 250 plus 150. So that's 350 centimeter cube. This is what they said. Assume that the volumes are additive, meaning that you can just add the volumes. Kevin, wouldn't that always be the case? Well, actually, if you go to university and you study anything with chemistry one day, you might come to a certain part where they teach you that some types of liquids in real life, it's very weird. But if you add them together, it doesn't add perfectly. So, for example, you'll add these two together, and then it would equal like 330. Which is weird, but what happens is that the liquids can sometimes almost fit into each other, and so the volumes are not additive. But I promise you, for any high school type of chemistry, the volumes are always going to be additive. Okay, so we know the volume of this container, and we also know the concentration of H3O. So we can use this formula to work out the moles of H3O. Once we have the moles of H3O, we can then work out how many moles of HCl there were after these two reacted. Because remember, these two are going to react first, and then whatever HCl is left over is going to ionize. Okay, so let's quickly go do that. So we can say 0.01 equals to the moles, which we don't know. Now the volume is 350, but we must change it to decimeters. So we are going to divide by 1000, and that'll be 0.35. Okay, so just go get the moles of H3O. So the moles of H3O is going to be 0.01 multiplied by 0.35. And that'll be 3.5 times 10 to the negative 3. Okay, so now we can look at this reaction over here. Make sure it's balanced. It is. And you can see that the mole ratio here is 1 to 1. So we can then say, therefore, the moles of HCl, so let's just make some notes for ourselves here. We can say, therefore, the moles of HCl after, or let's say remaining after this reaction over here, after this reaction, will be equal to 3.5 times 10 to the negative 3. Okay? So now think about this carefully. Now we know how many moles of HCl was left over after these two reacted. So what we can now do is we can now go work out the moles of HCl that we had in the very beginning of the question by using these two numbers over here. So we can go work out the moles of HCl originally, and that you can find by just saying C multiplied by V. So it would just be concentration, which was 0.03, multiplied by 0.2, because that's 200, so it's 0.2. And if you work that out, you end up with 6 times 10 to the negative 3 mole. So now you need to understand things carefully here. In the beginning, before the reaction started, any of the reaction started, from these two numbers, we can see that this is how much HCl we had. Okay? Then the NaOH and the HCl, they started fighting with each other and they started reacting with each other. Yeah? And we know that there was more HCl, there was leftover HCl. How much leftover HCl was there? Well, that's this number over here. So then what number could we work out now? Well, what we could now do is we could calculate if this is how much HCl we had in the beginning. After the reaction, this is how much we have. Then what could we calculate, guys? Well, we could calculate how much HCl was used when these two were reacting in this reaction over here. So we can now go say, how many moles of HCl did we use in reaction number 1? And that's going to be the original amount minus the amount that's left over. And if you calculate that, you end up with 2.5 times 10 to the minus 3. Okay, so now we know how many moles of HCl were used in this reaction. Now, we know that this one was the excess because there was leftovers. So that means this one is the limiting. What do we know about the limiting reactant? We use all of it. So now we can look at this reaction, which is already balanced. And if we know how many moles of HCl we used, remember, you're not going to use, for this part here, you're not going to use this number. You're not going to use this number. You're going to use this number because this is how much we actually used in this reaction. This number was just the amount of HCl that we have in the very beginning, which was over here. And this number was how much HCl was left over after this reaction took place. Okay. So we're going to use this much HCl over here. So then you can work out how much NaOH we used over there. And so the ratio is 1 to 1. So we can then say, therefore, the moles of NaOH used in this reaction 1 will be equal to 2.5 times 10 to the negative 3 moles. So now we know how many moles of NaOH we had in the very beginning. Because it's a limiting reactant, we use up all of it. So we know that the amount that we have here is the same as the amount we're going to use in the reaction because we're going to use all of it and there will be no leftovers of that one after the reaction. Okay, so now we know the volume of NaOH in the beginning and we know how many moles of NaOH there was in the very beginning inside here. And so we can now go use this formula again. So we can use C equals to N over V. And so we can go say the number of moles of NaOH was 2.5 times 10 to the negative 3 over its volume, which was 0.15 decimeters. Okay, and if you calculate this, you end up with 0.01, or you can actually write it in different ways. So 0.0167 moles per decimeter. You could also round it to, and this I'm getting from the memo, you could also round it to 0.017, for example, if you round to 2 decimals or 2 decimals over there. And then, or you can just round it to, you can round all of this up to 0.02 moles per decimeter. So you could give this as the answer, this is the answer, or this is the answer. All three of those were accepted. Here are all the questions that we will be looking at, but I will split them up so we have more space. Okay, so an electrochemical cell is set up using an aluminium rod and gas X. The initial EMF measured under standard conditions is 2.89. Okay, so it says state the standard conditions. Okay, so some learners, they get a little bit confused with STP, and then they get confused with that and standard conditions. So standard conditions, or let's start with STP. STP is when we are talking about gas, and we're talking about like molar volume, VM. And we typically have like a 22.4 decimeter number that comes up if we are at STP. Now, STP stands for 0 degrees Celsius, and then 1 atmosphere of pressure. When we are at standard conditions, which is what we do with electrochemistry, which is in the chapter of electrochemistry, then we are actually talking about 1 atmosphere of pressure, but then we're also talking about 25 degrees Celsius, not 0 degrees Celsius, okay? And then if there are gases present, there's the 1 atmosphere present. If there's gases, yep. And then all solutions must have a certain concentration, and that is 1 mole per decimeter. Like that. Okay, so don't confuse the two. STP is not the same as standard conditions. So here they say state the standard conditions under which the cell operates. So when answering the question, just say that the temperature is going to be 25 degrees Celsius. You can also say 298 Kelvin. For the pressure, you can just say 1 atmosphere. Some people also say 101.3 kilopascals. That's also okay. And then concentration, you're going to say 1 mole per decimeter. Okay, now this question says use a calculation to identify gas X. Okay, so we obviously need to go get our table. Now I did have to cut off this little piece here, but it just says aluminium and a gas. Okay, so the point is that we have aluminium. Now that is pure aluminium. That's not aluminium 3+. That is aluminium. So we're going to go circle that over there. Okay. Now we know that it is an electrochemical cell and it has a positive voltage. Does that mean that a reaction is happening spontaneously? Yes, it does. So it means that a reaction is happening. Okay. So if you're starting with aluminium, what is the only thing that can happen? Well, if a reaction is happening, the only thing that can happen is that it goes this way. It can't do anything else. You might say, yeah, but Kevin, doesn't the reaction go this way? But my answer is no, because then we would need to have aluminium 3+ to start off with. So this clearly means that we are going to have to go in that direction over there. Okay? So we know then that that is oxidation. So the aluminium is being oxidized. Okay, oxidation always happens at a anode, so that's the anode. So then I know that there's this formula to calculate my cell potential, and it goes cathode minus anode. They tell us what the cell potential is. I don't know the cathode, but I know my anode value is negative 1.66. Okay, so that would end up becoming a plus 1.66. Okay, now you're going to go solve for your cathode by taking the 1.66 over to the left, and we end up with 1.23 volts. So now we just go down to 1.23 volts, and I don't even have that on my table. Just give me a second. And so here I've got some lower down values on the table. Now I know that if one of my materials started over here, then the other one, because you get redox, so you get oxidation and reduction. So if this one is on the right-hand side of the table, then the other substance is on the left. So I go down to 1.23. There's 2 things over there. I only focus on the left, and I look for any gas. See any gas? There it is. Oxygen is in the gas phase. So the gas would literally be oxygen. Okay, so for the next questions, I'm just going to go write this reaction down. Now remember, this reaction would start on the left because this one started on the right, because you have to get one of them being oxidized and one of them being reduced. So one goes to the right, one goes to the left. So we're just going to go write that down. Okay, so for that aluminium reaction, I'm just going to write it. I know that on the table it looks like this, like that, but I'm just going to write it in the correct order. So we said that it was the aluminium becoming aluminium 3 plus 3 electrons, okay? And we're not going to put a double arrow because on the table it's a double arrow, but that's just them trying to show us that these reactions have the potential or the ability to go left and right. But we know that in our reaction it started with aluminium. So I'm also making it start with aluminium. Okay, and then the other reaction, I wrote it down here, was oxygen plus 4H plus 4 electrons turning into 2H2O. Okay, so this question says write down the formula of the reducing agent. Now the reducing agent, if you remember, is the substance that is oxidized. Now, if you look at these two reactions, we know that oxidation is this one over here, where you've got the electrons on the right-hand side. Remember, if the electrons are on the right-hand side, that's oxidation. If the electrons are on the left-hand side, that is reduction. Let's write that down. If the electrons are on the right, that is oxidation. And then if the electrons on the left, that is reduction. Okay? So the substance that is oxidized is in the reaction where the electrons are on the right. So that's this one. Okay, so how do we know which one is the oxidation, the reduction agent? You always look at your reactants. Your reactants are these ones and these, or not the electrons, these ones. Okay, it's always the things before the arrow. Those are your reactants. Okay, so we said that the substance that is oxidized, the reducing agent is the substance that is oxidized. So we go to the oxidation reaction, and so this over here is going to be our reducing agent. So we can just say aluminium. This question says write down the half reaction. These are half reactions that takes place at the cathode. Okay, so we know that cathode is reduction. That's where reduction happens, and reduction is when the electron's on the left, and so this is the answer for this question. This question says write down the cell notation. So remember, with cell notation, oh yes, and we know that this is a gas. Okay, so with cell notation, we know that you're always going to put, so you're going to have a salt bridge, okay, over there, and then you're going to have all the different phases of your anode, and then all the different phases of your cathode. So in your anode, you're going to have, so you always put your solid first, so you're going to have aluminium as your anode. Remember we said this is the anode, where oxidation happens, and then this is the cathode, where reduction happens. Okay, so we're going to start off by saying aluminium in the solid phase, then you're going to put a line. Now you're going to look for any gases. Are there any gases in this one? No, there's not. And then you're going to look for any aqueous species. Aqueous species are the ones that are going to have this charge over here, and so you're going to say Al3 plus in the aqueous phase. Now, some learners are under the impression that over here, you have to go say 1 mole per decimeter. You don't have to. In fact, you don't even lose marks if you leave out the AQ part. You don't even have to put that in if you don't want to. You don't lose marks, okay? Right, now we go to the next part, which is this one over here. Now, this one's going to be really interesting because we've got substances that are aqueous, we've got substances that are gases, and then water is always in the liquid phase. Now, what's interesting is there's no solid. So what do you do when there's no solid? Because there has to be a solid. If there's no solid, then you need to use platinum, okay? And that'll always be the one at the very end. So platinum, like that. Okay, then we're going to look for, now we've got a whole bunch of different phases here. We've got liquid, aqueous, and gas. So we are going to go show all of those, and then we're going to use a phase boundary in between. So in between that, and then it doesn't really matter. So like, let's say, for example, we can say, let's take the liquid, for example. So that's going to be H2O. That's in the liquid phase. Another phase boundary, H plus, which is the hydrogen ion, which is in the aqueous phase. Phase boundary, oxygen, which is in the gas phase. So this is quite a challenging one because it's not the normal. Usually we just end up with like a solid and an aqueous substance, but now we have all of these different phases over here, okay? And then remember, if there's no solid, there has to be a solid, then you would rather just use platinum, because platinum is, it's a metal, but it's non-reactive. So it's highly stable, so it can be used with these chemicals over here, and it won't get involved in the reaction. This question says, which container, zinc or copper, will be more suitable to store an aqueous solution of nickel ions? Refer to the table, which I'll get now, to fully explain the answer in terms of the relative strengths of reducing agents. Okay. So what we need to do is we're going to say which container, zinc or copper, will be more suitable to store an aqueous solution. Okay, so let me show you something here. Let's quickly go and separate this. And let's say we've got a container. Okay. Now this container is made of zinc, for example. So it's a zinc metal container. And in there we've got a solution of nickel ions. So it's probably some solution with, it's a liquid solution, but it's got these, aqueous, if you want to be specific, but it's a solution that's got some ions of nickel inside them, okay? And then here in this one, you've got a copper, pure copper metal, let's say Zn over here, and let's say Cu over here. And then we've got this nickel ion solution. Now think about this. You have a garage at your house and you've got this nickel ion solution that you would like to put into the container because maybe you use it for certain things and now you finished working for the day, so you want to pour this nickel solution into a container. Now when you get to your garage the next morning, when you open this container, what would you want to see? Well, you would still want to see your nickel solution, right? What you won't want to see is some type of chemical reaction that's busy taking place and it's causing your nickel 2+ to disappear, because that can happen if you put the liquid in the wrong container. So what we're going to go do is we are going to go try see. We're going to go set up a galvanic cell with this one, and we're going to go calculate the voltage or the EMF, and then we're going to do the same with this one. And we are going to look for the one that does not have a spontaneous reaction. So we're going to look for one that gives us a negative EMF, because a negative EMF or voltage value means non-spontaneous, and it means that a chemical reaction will not take place spontaneously. Okay, so we're going to go get our table, and let's start with this one. Okay, so here we have the table. Now pretty much you're just going to go find this on the table. So nickel 2+, there it is. And I'm using table 4B, by the way, because that's the most popular one. And then you need to go find zinc. Not zinc 2+, zinc, specifically zinc. There we go. Okay, now we are going to pretend that a reaction is going to happen. So if a reaction is going to happen, then the only thing that this zinc can do is go that way. There is nothing else it can do. It can't go that way. Where's it going to go? So if a reaction does happen, it's going to go that way. And if this one does react, it's going to go that way. So we're pretending that a reaction will happen. And now we're going to go calculate the voltage. So you should know that when the reaction is written like this from left to right, that's reduction, okay? So this is your reduction reaction, meaning that this is your cathode. And then this, when it's written in this direction from right to left, that is your oxidation reaction, and that is your anode. Now to calculate your cell value, we always know that there's a formula that says cathode. This is on your formula sheet, by the way, minus your anode. And so your cathode voltage value is negative 0.27. Subtract your anode value, which is negative 0.76. And so if you had to work this out, we end up with 0.49 volts. So this means that a chemical reaction is going to take place, and that is not good, because what that means is that this nickel 2+ is going to convert into pure nickel. So when you come and look at your solution in the morning, you're going to see solid nickel instead of liquid nickel, like aqueous nickel. And so a chemical reaction did take place because this is a positive value, and so that means it's spontaneous. Now, when you give your answer, you don't really have to go and show any of this over here, okay? This is just me showing you how to figure this out, because some learners are really good at just saying increasing, oxidizing, increasing, reducing. So a lot of learners struggle with that. So let me just show you how to use this calculation, and then once we have our answer, I'll show you what you actually need to write in the exam to get your 4 marks, okay? If they said show your calculations and stuff, then you would use this method. But they asked us to use the relative strengths of reducing agents. So I'll show you what to do now. But let's just quickly go do this one and see how this one would have worked. Okay, so I went and replaced the table with, so we've got now nickel 2+ with this one. So let's go circle that. And then we've got pure copper. Now learners struggle with which copper to use. We don't really use, we're not going to use this one because this is not copper. This is copper iron. It's copper plus and it's copper 2+. But what we have here is a pure copper container, so that's pure copper. There we go. And so let's pretend that a reaction does happen. So this one would go this way, this one would go this way. Okay, and so we know that when the reaction is written like that, that is reduction, and when a reaction is written like this is oxidation. So when there is reduction, then this is your cathode, and then when there's oxidation, that is at your anode. So if you had to go work out the cell value now, you're going to get cathode minus anode, and so that's going to be cathode, negative 0.27 minus 0.34, and that's going to give us negative 0.61 volts. So look at that, it's a negative value. What that means is that this reaction will not actually take place spontaneously. So if you wanted to store your nickel solution in a copper container, that would be a very good idea, because the reaction will not happen by itself. It's got a negative value, meaning that this reaction is non-spontaneous, so it won't naturally happen. Okay, now how do we write this answer in a test? Because they asked us, they didn't say use the calculation, they said in terms of relative strengths of reducing agents. Okay, so we're going to say that the answer is copper. Okay, copper. But now for 4 marks, we have to try and explain why without using the calculations that I just showed you. That was just to give you an idea of how to see it. But we've got to use relative strengths of reducing agents. Okay, so here's the reducing agents on the right-hand side. And then on the left-hand side, that is oxidizing agents. Okay, so let's start with zinc. Okay, and let's compare it with nickel. I know that in our reaction we had nickel 2+, but we still need to compare these two with each other because they are reducing agents. Now, when you follow this arrow, the arrow goes, this arrow here, goes upwards. So as it goes up, the strength of the reducing agent becomes better. So who's the better reducing agent between zinc and nickel? It's going to be zinc. So we can say that zinc is a stronger reducing agent than nickel. So think about that. Zinc is a stronger reducing agent. So that means that the zinc will reduce the nickel. So it'll cause this nickel to be in a reduction reaction. So it'll cause this reaction to go like that. So therefore, zinc will cause Ni2+ to be reduced to nickel. Now that would not be a good thing in this reaction over here when you take the nickel and then it gets reduced into pure nickel. That's not what we want to happen, and this is why we don't want to use zinc. Now let's go explain why copper will not be a problem. So remember, we're not going to use this copper because that has a plus. We want to use pure copper, so we're going to use this one and we're going to use the nickel. Now all of a sudden we can see that who's the stronger reducing agent? Now nickel is the stronger reducing agent. So what that means is that we can say copper is a weaker reducing agent than nickel. So therefore, copper will not be able to reduce the Ni2+ to Ni. So it won't be able to cause this reaction to become a reduction reaction. It won't be able to cause this to be reduced to nickel. Okay? And that's a good thing. Because it can't reduce the Ni2+ to nickel, then that means that the Ni2 plus will stay Ni2 plus, and that's what we want. All right, so with this question, there will be more questions on the next slide, okay? So it says, well, let me just quickly show you what other questions we have. So we have these ones here, and then these ones, and then these ones. Okay, so it says the simplified diagram below represents an electrochemical cell used for the electrolysis of concentrated. That word might be important. Remember, we've spoken about concentrated and dilute when they use those words and what that means. Okay, it might not come up, but just look out for that. Used for the electrolysis of concentrated sodium chloride solution. Okay, so because they're not using, remember I've spoken to you guys about this. You get, for example, aqueous, and then you get molten. And when we said it was molten, then there's no water. But when it's aqueous, then we are using water. So there is also water inside here. I'm not sure if that's going to become a factor, but just remember that, okay? So water is also there. So this question says, define the term electrolysis. Well, I'll give you the definition now, but electrolysis is when you use electricity to be able to do some type of chemical change. Okay, so the correct definition, well, there was a few, but one of them was, it is the use of electrical energy to produce a chemical change. This one says that chlorine gas is released at electrode X. Okay, electrode X is chlorine gas being given off. Chlorine is a diatomic molecule. Oh, they did tell us it's Cl2. Okay. Write down the letter X or Y where oxidation takes place. Okay, so we know that oxidation always takes place at an anode. That is whether we are looking at a galvanic cell, a galvanic cell, which is not this one, or this one, which is electrolytic. So galvanic or electrolytic, oxidation means anode. And then reduction is where you have your cathode. Okay, so let's think about this. If you look at NaCl, we know that that is actually Na plus and Cl minus. Okay, now they tell us that the Cl minus got oxidized or reduced over here, okay, at this electrode over here. So we converted Cl minus to Cl2. So let's go get our table now. And so what we have is we have Cl minus being converted into Cl2. So you need to know that when a reaction goes that way, where you've got electrons on the left-hand side like that, that is oxidation. That is oxidation. And so if we can see there's oxidation, now they said letter X or Y of the electrode where oxidation takes place. Well, this is oxidation, so you can just say X. Now it says, what is the half reaction that takes place at electrode Y? Okay, so now we've got to be careful because of the water. So I have explained this to you guys before, where we have the electrolysis where there's water presence, electrolysis of aqueous solutions. And so what we do is we look at this Na+. Now, where is that on the table? Well, there it is there. Okay, so that means we are on the left-hand side of the table. And so if you've watched those lessons, you'll know that when you are looking at that one, then to see if the water is gonna win, you have to use this water over here. This is the water that we use in grade 12 on the left-hand side of the table. Remember, I have showed this in previous videos. And then if you are on the right-hand side of the table, then there is a water that we use, but that's way further down on the table, okay? So I have shown that in previous lessons. So to see who wins over here, you literally just look at the arrow, and we can see that as you go down, it becomes stronger, increasing strength, okay? So that means that the water is actually going to win. So over here, water is going to react according to this reaction. So a lot of learners would have gotten that wrong. They would have just gone and used the Na because they didn't realize that this one is a aqueous solution, okay? The concentrated part only affects if you've watched my video where I explain aqueous solutions, the concentrated part is only going to affect the Cl minus if they ever asked us about that. But I don't think they're going to. So it says that, let's go just write this down. But what's important is the aqueous part. It means that there is water present. They didn't say molten. Okay, and that's going to give us H2, which is a gas, plus 2OH minus. Okay. This question says, write down the direction in which the electrons flow in the external circuit, which is this one over here. All right, so let's just see what's happening here. We know that here we are converting from Cl minus to Cl2. And then at this electrode, we just worked out that the reaction was, I've just written it down here, 2H2O plus 2 electrons. Let's just write this better. 2H2O plus 2 electrons gives us hydrogen plus 2OH minus. And then let's just go right down this one. Just be careful. We are going from Cl minus to Cl2. So we are going from Cl minus to Cl2. So we're going to write it starting with this part, and then we're going to write this part as the product. Okay, so now by analyzing this, we will be able to get an idea of whether the electrons are going to go this way or whether the electrons are going to go this way. So listen up carefully. So if you look at this reaction over here, it says that the 2Cl minus, which we know is floating around here, is going to be converted into Cl2, which goes off as a gas, and there will also be 2 electrons. That means 2 electrons are going to be released on this side. Those 2 electrons are then going to travel through this wire to this other side over here, where they will then be used up over there. So it says that there will be 2 H2O molecules, which is floating around in the water over here. It'll then take those 2 electrons, which are coming over here, and it will convert those 2 things into that. So the electrons are going from X to Y. So we're going to say X to Y. Okay, this question says, what is the balanced equation for the overall reaction that takes place? Okay, so what we do now is we take these 2 reactions that we have, and we just make sure that the electrons are the same first of all. Yes, they are, which is great. And now we just add the 2 reactions together. So you just put an arrow. Now everything that's on the left of the arrow, you can put together. So that's going to be 2H2O plus 2E minus plus 2Cl minus. Okay? And then you put everything that's on the right of the arrow. So this, and this, and this. So that's H2 plus 2OH minus plus Cl2 plus 2E minus. And now these 2 would cancel out, and that's what we want. And there's your final answer. Whoops, take away that plus. This question over here says, how will the pH of the electrolyte, which is the solution, change? Now, let's just go get our reaction that we got now. The overall reaction we said was 2H2O. The reaction after we balanced it, so it's 2H2O plus 2Cl minus gives us hydrogen plus 2OH minus plus Cl2. So whenever we talk about pH, we need to think about the 2 main components, which is H3O plus and OH minus. So when you have a lot of this, so when this one goes up, your pH goes down. Because remember, this is what acids make. Whenever acids ionize in water, they produce H3O plus. And so when that amount goes up, the pH goes down because acids have a low pH. When this amount goes up, your pH goes up. Okay? Because OH minus is what bases produce. So what we can see in the product, if you look on the right hand side, there's products. There are OH minuses. So as this reaction is going, the OH minus concentration is going up. So what would happen to the pH? It would increase. And then our reason would be that the OH minus concentration is increasing, or let's say increasing.